The blackout. What's happening right now behind the Sun? The interstellar object 3I-ATLAS, the third visitor from beyond our solar system, is behind the Sun right now, hidden. And Avi Loeb's warning echoes louder with each passing hour. If you want to take a vacation, take it before October 29th, because who knows what will happen. Those words aren't some distant forecast anymore. They're about the next 4 days, about what's happening at this very moment, 135 astronomical units from the Sun while you're listening to this. 3I-ATLAS reached solar conjunction 4 days ago on October 21st, positioning itself on the exact opposite side of our star from Earth, invisible to every telescope we have, and in exactly 4 days on October 29th it hits perihelion, the closest point to the Sun in its trajectory, the moment when 33 gigawatts of solar radiation will hit its surface. That's a third of the total power output of every nuclear reactor in the United States combined, bombarding an object that Harvard scientists think might not be a comet at all, but something far more significant. Before we go further, if you've been following the 3I-ATLAS story and want to stay updated on what happens in these critical 4 days, hit that like button and subscribe so you don't miss what we discover when this thing emerges from behind the Sun in November. And for today's episode we've added some calm background music, so let us know in the comments if you like it. Plus tell us where you're listening from, what time it is there, and whether you think we're watching First Contact unfold in real time. Share this on social media, and hit that hype button to help our community grow. Thank you so much for your support. So let's talk about what makes these 4 days so critical. The timing here isn't just unusual, it's statistically improbable to the point of absurdity. Loeb and his team calculated that the probability of 3I-ATLAS achieving perihelion while positioned on the exact opposite side of the Sun from Earth, within a solar elongation of 30 degrees, is roughly 7%. Not terrible odds on their own. But that's just one data point in a cascade of improbabilities that multiply into something far more disturbing. Think about what an Oberth maneuver actually is for a moment. It's one of the most elegant tricks in orbital mechanics. When a spacecraft is moving at its maximum velocity, which happens at the closest point to a massive body like the Sun, any thrust it applies gets amplified. The kinetic energy gained is proportional to the velocity at which the thrust is applied. Fire your engines when you're already screaming through space at maximum speed, and you get far more bang for your buck. It's why every interplanetary mission uses gravity assists. It's basic astronautics. And the optimal point for a reverse Oberth maneuver, where you want to slow down and stay bound to the Sun instead of escaping into interstellar space, is exactly at perihelion. Now here's where it gets interesting. 3I-ATLAS will be executing this maneuver, if it is a maneuver, during the only window when Earth-based telescopes can't see it. The Sun blocks our view completely. We're blind. If something wanted to perform a clandestine trajectory change, to slow down, to deploy probes, to alter course toward inner system planets, this would be the perfect moment, and we won't know until it emerges on the other side in early November. The energy budget available during this window is staggering. 33 gigawatts hitting a surface with a minimum diameter of 5 kilometers. That's not speculation, that's basic physics. Solar irradiance at 135 astronomical units, spread across that surface area. If this object has any kind of technological capability, any way to harvest or utilize that energy, perihelion is when it would do so. It's the one moment in its entire trajectory through our solar system when maximum power is available. Loeb posted on his Medium blog just 3 days ago, on October 22nd, laying out exactly why this moment matters. He's calling it a potential black swan event, a low probability occurrence with massive implications. He writes that as of now, 3I-ATLAS appears most likely to be a natural comet, but that the remote possibility of an Oberth maneuver must be considered seriously because of its huge implications for humanity. Those are careful words from someone who's been burned by the media before, who's been called reckless and attention-seeking by his colleagues, but he's not backing down. The International Asteroid Warning Network activated a monitoring campaign on October 27th. That's 2 days from now. The campaign runs through January 27th, 2026. 3 months of intensive observation. This is not standard protocol for comets. The IAWN is designed for potentially hazardous asteroids, for objects that might impact Earth. They don't waste resources on every icy visitor from beyond the solar system. The fact that they're treating 3I-ATLAS as a planetary defense matter tells you something about what's happening behind closed doors. Someone, somewhere, thinks this warrants the infrastructure we built to save civilization from extinction-level impacts. Let's talk about what we're actually looking for when this thing emerges. If 3I-ATLAS continues on a purely gravitational trajectory, if it behaves exactly as celestial mechanics predicts, it will pass closest to Earth on December 19th at a distance of 269 million kilometers. That's about 1.8 astronomical units. Not close by any means, but close enough for detailed observation. Then, on March 16th, 2026, it swings past Jupiter at 54 million kilometers. The Juno spacecraft will have a front row seat. The European Space Agency's JUICE mission will pass within 64 million kilometers on November 4th, just days after perihelion. These aren't planned encounters. These are targets of opportunity, but they're extraordinary ones. Here's the key. If the trajectory changes, if 3I-ATLAS shows any deviation from the path gravity alone would dictate, we'll see it in the orbital elements. Astronomers will measure the position and velocity as it emerges from behind the Sun and compare it to predictions. Any discrepancy, any non-gravitational acceleration, any alteration in the orbit, and we have our answer. Not proof of aliens necessarily, but proof that something other than gravity and solar radiation pressure is acting on this object. And solar radiation pressure can only push things away from the Sun. It can't slow them down. It can't perform a reverse O-berth. If this thing slows down, if it sheds velocity in a way that keeps it bound to the solar system, instead of shooting back out into interstellar space, there's no natural explanation that holds up. The paper Loeb co-authored with Adam Hibbard and Adam Krul from the Initiative for Interstellar Studies lays out the scenarios in detail. Its title is the Interstellar Object 3I-ATLAS Alien Technology, and it's not a joke. It's a rigorous astrodynamics analysis using interplanetary trajectory software, calculating the delta-v requirements for various maneuvers. If 3I-ATLAS wanted to intercept Earth, the optimal arrival window is late November to early December 2025. That's 6 to 7 weeks from now. The delta-v required depends on when the burn happens, but if executed at perihelion, during the blackout the fuel requirements drop dramatically. Efficiency matters when you've travelled light years. But there's another scenario that's almost more unsettling. What if it doesn't intercept Earth directly? What if the mothership, as Loeb calls it, continues on its gravitational path and simply releases mini probes? Small spacecraft, maybe the size of intercontinental ballistic missiles, with their own propulsion. The delta-v needed to reach inner planets from 3I-ATLAS's trajectory is surprisingly low. Less than 5 kilometers per second for Mars, less than 5 for Venus, less than 5 for Jupiter, until November. Those are speeds we achieve with chemical rockets. If you wanted to send exploration probes to every significant body in the solar system, this trajectory is almost ideal. You cruise through the outer system, sweep past the inner planets, and you're positioned to release payloads at minimal cost. Think about that for a moment. The trajectory 3I-ATLAS is following isn't optimized for speed. It's not a straight shot through the solar system and out. It's aligned to within 5 degrees of the ecliptic plane, the disk where all the planets orbit. That alignment has a probability of about 0.2% for a random interstellar object. But if you wanted to visit planets, if you wanted access to multiple worlds with minimal maneuvering, you'd choose an ecliptic-aligned path. You'd give yourself options. The timing of the Mars flyby adds another layer. 3I-ATLAS passed within 190 million kilometers of Mars on October 3rd. That's close. Multiple spacecraft orbiting Mars turned their instruments toward it. NASA's Mars Reconnaissance Orbiter has a camera called HiRISE, the High-Resolution Imaging Science Experiment, with a pixel resolution of 30 kilometers at that distance, 3 times better than the best images from Hubble or the Keck telescopes. HiRISE captured 3I-ATLAS as it passed, and those images haven't been released. Not publicly, not even to the scientific community in any detailed form. Loeb has been asking for them. He's mentioned it in multiple blog posts. NASA's silence on this specific point is deafening. The European Space Agency, in contrast, has been relatively transparent. The ExoMars Trace Gas Orbiter imaged 3I-ATLAS and released the data. It shows a classic cometary appearance in those frames, a fuzzy white dot with a small tail. Comforting, right? Except the emission patterns in the spectroscopic data don't match any known comet. The ratios are wrong. The chemistry is off. And that brings us to the nickel. Keck 2 telescope data from Hawaii, published just last week, shows that 3I-ATLAS is emitting nickel in ratios to iron that don't occur naturally. On Earth, this signature only appears in industrially produced nickel alloys, created through the carbonyl chemical pathway. You refine nickel by forming and decomposing nickel tetracarbonyl. It's a process we invented for metallurgy. The paper's authors argue that this carbonyl process could happen naturally near the nucleus of 3I-ATLAS, that conditions there might spontaneously create these compounds. But that explanation requires a very specific set of circumstances that we've never observed in any other comet, including 2I Borisov, the previous interstellar visitor that everyone agrees was natural. The nickel is concentrated in a region extending out to an exponential radius of 600 kilometers from the nucleus. Cyanide, another emission detected, extends to 840 kilometers. These are trace-out gassing rates, grams per second rather than kilograms, but the spatial distribution is strange. Why would nickel be more concentrated near the center than cyanide? If both are sublimating from ice, they should follow similar patterns based on volatility and solar heating. They don't. The nickel acts like it's part of a structure, not a diffuse coma. Horace Drew, a retired researcher from Australia's Commonwealth Scientific and Industrial Research Organisation, looked at the Mars images and said flatly, "It's not a comet." He pointed to the green glow visible in enhanced versions of the images. That green, he argues, is consistent with nickel emission, and aliens may coat their spacecraft with nickel just as we coat ours. It's a bold claim from someone with legitimate credentials, even if he's outside the mainstream consensus, and it raises the question, why would nature choose nickel as a coating? Why would an icy body concentrate this specific metal in its outer layers? The counter-argument is that we're seeing what we want to see. That comets are diverse, that interstellar comets especially might have chemistries we don't understand because they formed in other stellar systems with different compositions. That every weird feature of 3I-ATLAS, from the nickel to the antitail to the trajectory, is just a pile of coincidences. Unlikely coincidences, sure, but coincidences nonetheless. And to be fair, that's probably true. The universe is big, weird things happen, 1 in a million chances occur constantly when you're sampling billions of events. But here's the thing, we're not sampling billions of events, we're sampling three interstellar objects detected in human history. One Oumuamua in 2017, which had its own unexplained non-gravitational acceleration. 2I Borisov in 2019, which looked and acted like a normal comet and didn't raise any eyebrows. And now 3I-ATLAS, which is breaking every pattern. When your sample size is 3 and one of them is screaming anomaly, you pay attention. Loeb has created what he calls the Loeb scale, a ranking system from 0 to 10 for how likely an interstellar object is to be technological. 3I-ATLAS currently ranks 4. That's not proof, it's not even strong evidence, but it's enough to justify serious investigation. He's clear that the rank will change based on post-perihelion observations. If 3I-ATLAS continues on a normal trajectory, shows typical cometary activity after the intense solar heating, acts exactly as a dirty snowball should, the rank drops to 2. The mass and ecliptic alignment anomalies remain, but they become isolated oddities rather than part of a pattern. If, on the other hand, the trajectory changes, if non-gravitational accelerations appear, if the chemistry gets weirder, the rank climbs. Right now, as you're listening to this, on October 25th, 2025, that object is behind the Sun. It's closer to our star than Earth is, moving at 68 kilometers per second at perihelion. The surface temperature is spiking. If it's ice, it's sublimating furiously, releasing volatiles, building up coma and tail pressure. If it's rock, it's absorbing more energy than it has at any point in millions of years. And if it's something else, if there's any kernel of truth to the technological hypothesis, then it's executing maneuvers that will determine whether humanity is alone in the universe. We'll know in November. The blackout ends. Telescopes around the world will acquire it again. The trajectory will tell the story. Until then, we're in the dark. Literally. And the question isn't whether aliens are coming. The question is whether we're watching them arrive, and we just don't know it yet. Because if Loeb is right, if even half of what he's suggesting has merit, then the next visitor isn't late November. The next visitor is already here, hiding behind the Sun, counting down the hours until it can move. And we have 4 days left to wonder what happens when the clock hits 0. The IAWN activation Why Planetary Defense Woke Up. There's a document you need to know about. It's an editorial notice from the Minor Planet Center published just days ago, announcing something that should make every person paying attention to 3I-ATLAS sit up straight. The International Asteroid Warning Network has initiated a monitoring campaign specifically for this object. The campaign began on November 27th. Wait, let me correct that. The campaign begins on October 27th, that's 2 days from now, and runs through January 27th, 2026. 3 months of coordinated global observation using the infrastructure we built to prevent extinction-level asteroid impacts. And here's what nobody's saying out loud. The IAWN doesn't do this for comets. Let me be very clear about what the International Asteroid Warning Network actually is. It's not some academic research group. It's not a collection of amateur astronomers sharing telescope time. The IAWN is a planetary defense mechanism established under the United Nations Committee on the Peaceful Uses of Outer Space. It exists for one purpose: to detect, track, and characterize objects that pose an impact threat to Earth. When the IAWN activates a formal monitoring campaign, it means someone, somewhere in the decision-making chain, has classified an object as worthy of the resources we reserve for potential civilization enders. They don't waste these assets on scientific curiosities. They don't deploy planetary defense protocols for interesting comets. So why 3I-ATLAS? The official line is that it's an unprecedented opportunity to study an interstellar object with multiple spacecraft in favourable positions. JUICE will fly within 64 million kilometres on November 4th. Juno gets close to it near Jupiter in March. The geometry is good, the science return would be valuable, and we should take advantage of targets of opportunity. That all sounds reasonable until you look at what happened with 2I Borisov. That was also an interstellar comet. That also passed through our solar system with spacecraft nearby. The IAWN didn't activate for Borisov. The Global Defense Network didn't spin up. Astronomers observed it extensively, sure, but through normal channels, normal prioritization. Borisov was interesting. 3I-ATLAS is something else. The timing of this activation is what keeps me up at night. The campaign starts October 27th, which is 2 days before perihelion. They're not waiting to see what happens. They're positioning assets in advance. That suggests the decision was made based on pre-perihelion data, based on the anomalies that were already visible. The trajectory alignment, the size, the nickel emissions, the anti-tail phenomenon, all of that was enough to justify treating this as a potential threat scenario. Not a confirmed threat, but potential. And in planetary defense, potential is enough. You don't wait for confirmation when the cost of being wrong is existential. Here's where it gets complicated. The IAWN's mandate is impact threats. 3I-ATLAS is not on a collision course with Earth. Its closest approach in December will be 1.8 astronomical units away. That's more than the distance between Earth and Mars at their closest. There is zero chance of impact. None. The trajectory is well characterized. The orbital elements are known to high precision, and unless something changes dramatically, this object will pass through the inner solar system and head back out toward interstellar space without coming anywhere near us. So why activate impact threat protocols for something that can't impact us? There are two possibilities, and neither one is comforting. The first is that the IAWN has expanded its interpretation of threat to include non-impact scenarios. If an object showed signs of being artificial, if there was even a credible possibility of technological origin, that would constitute a different kind of threat. Not kinetic, not a rock falling from space, but intelligence, contact. First contact protocols fall under a completely different bureaucratic structure than asteroid deflection, or at least they're supposed to, but maybe the lines are blurring. Maybe when you're staring at something that might be an alien spacecraft, you use whatever tools you have available, and the tools we have available are telescopes pointed at dangerous rocks. The second possibility is that they know something we don't, that there's data, observations, measurements that haven't been made public, that the full picture looks different from inside the network than it does from outside. And before you dismiss that as conspiracy thinking, remember that NASA still hasn't released the high-rise images from Mars Reconnaissance Orbiter, the most detailed photographs of 3I-ATLAS in existence, taken at 30-kilometre pixel resolution as it flew past Mars on October 3rd, are sitting in an archive somewhere, and nobody outside the agency has seen them in any meaningful form. Why? What's in those images that requires restricted access? Avi Loeb has been publicly asking for those images. He's emailed NASA directly. He's written about it in his blog posts. The silence in response is conspicuous. And just this week, in a blog post dated October 24th, Loeb escalated his language. He's now directly accusing NASA of burying the evidence while praising the European Space Agency for being more honest about their findings. Those are strong words from someone with Loeb's position in the scientific community. He's not some fringe blogger. He's a Harvard professor, former chair of the astronomy department, former member of the President's Council of Advisors on Science and Technology. When he says one space agency is covering up data while another is being transparent, people notice. The ESA has been relatively open. ExoMars Trace Gas Orbiter data was released. The images show what looks like a comet, fuzzy coma, small tail, nothing obviously artificial. But spectroscopic analysis from that same data shows emission lines that don't match known comets. The chemistry is wrong. The abundances are off. ESA published it anyway. NASA, in contrast, has been nearly silent. Tom Statler, NASA's lead scientist for solar system small bodies, gave one quote to The Guardian. "It looks like a comet. It does comet things." That was it. No detailed analysis, no data release, no engagement with the specific anomalies Loeb has been documenting. Just a dismissal. Now maybe that's appropriate scientific caution. Maybe NASA doesn't want to fuel speculation by engaging with every unusual measurement. The agency has a credibility problem when it comes to UFOs and aliens. Decades of dismissals and debunking have trained the public to assume NASA knows more than it says. Whether that's fair or not, it's the reality. So when NASA goes quiet on something this high profile, people fill the silence with their own interpretations. And Loeb is handing them material. His blog post from October 22nd lays out 8 anomalies that he says justify a rank of 4 on his Loeb scale. We covered some of these already, but let's go through the full list, because this is what the IAWN is responding to. This is the evidence stack that triggered planetary defense protocols. First, the orbital plane alignment within 5 degrees of the ecliptic, probability 0.2%. Second, the sunward jet or antitail observed in July and August, which is not a perspective illusion like it is with normal comets. Third, the mass being about 1,000,000 times larger than Oumuamua and 1,000 times larger than Borisov while moving faster than both, probability less than 0.1%. Fourth, the arrival time fine-tuned to bring it within tens of millions of kilometers of Mars, Venus and Jupiter, while being unobservable from Earth at perihelion, probability 0.005%. Fifth, the gas plume containing much more nickel than iron, found in industrially produced alloys, with a nickel to cyanide ratio orders of magnitude larger than all known comets, including Borisov, probability below 1%. Sixth, the gas plume containing only 4% water by mass when water is a primary constituent of familiar comets. Seventh, extreme negative polarization unprecedented for all known comets, including Borisov, probability below 1%. Eighth, arrival from a direction coincident with the WOW signal to within 9 degrees, probability 0.6%. That last one deserves unpacking because most people have forgotten about the WOW signal connection. In August 1977, the Big Ear radio telescope at Ohio State detected a strong narrowband radio signal that lasted 72 seconds. It was so unusual, so clearly not natural background noise, that the astronomer on duty wrote WOW in the margins of the printout. The signal came from the direction of Sagittarius, near the constellation's border with Ophiuchus. It never repeated. Decades of follow-up observations found nothing. The most likely explanation is still some kind of terrestrial interference, or a passing satellite, but it remains unexplained. And 3I-ATLAS's incoming trajectory, when traced back through space, points to a region of sky within 9 degrees of where the WOW signal originated. 9 degrees is a huge area on the celestial sphere. The probability of a random interstellar object passing through any given 9-degree patch is about 0.6%. Not impossible, not even particularly unlikely on its own. But stack it on top of the other 7 anomalies and the coincidences start to strain credulity. If you were to multiply all these individual probabilities together, assuming they're independent, you get a cumulative likelihood lower than 1 part in 10 quadrillion. That's the number Loeb keeps citing, 1 in 10 to the 16th power. Of course, these probabilities aren't truly independent. The ecliptic alignment affects flyby geometry, which affects timing, which affects observability. You can't just multiply them naively. But even if you're generous with correlation factors, even if half of these are explained by the same underlying cause, you're still looking at odds that make lottery winners look common. The IAWN sees these numbers. They have access to all the data, all the measurements, all the trajectory analyses, and they made a decision. Activate the network. Treat this as a priority. Commit resources for 3 months of intensive monitoring. That decision didn't come from nowhere. It came from people looking at the same evidence we are, and concluding that the possibility, however remote, requires a response. Because the consequences of being wrong in one direction are negligible. If 3I-ATLAS turns out to be a weird comet and we spent 3 months watching it closely, we wasted some telescope time and learned interesting things about interstellar chemistry. If it turns out to be something else and we weren't watching, we missed first contact. We missed the most important event in human history happening in real time. There's a Brookings report that gets referenced in UFO circles, a study from 1961 commissioned by NASA about the implications of discovering extraterrestrial life. One of its conclusions was that public announcement of such a discovery could cause severe psychological and social disruption, particularly if the discovery involved artifacts or intelligence rather than simple microbes. The report suggested that controlled release of information might be preferable to immediate disclosure. Whether NASA or any other agency actually follows those guidelines is unknown, but the framework exists. The idea that first contact might be managed rather than announced is baked into institutional thinking. So when Loeb accuses NASA of burying evidence, he's tapping into that decades-old suspicion. Maybe there's nothing to hide. Maybe high-rise images just aren't that interesting, and releasing them requires bureaucratic processes that take time. Or maybe someone looked at those images and saw something that required a different kind of response. A quiet response. An IAWN activation without public explanation. A monitoring campaign framed as scientific opportunity rather than threat assessment. You can't know. That's the frustrating part. The evidence is ambiguous enough that both interpretations fit. What we do know is that starting in 2 days, on October 27th, the most sophisticated asteroid tracking network humanity has ever built will be pointed at 3I-ATLAS continuously for 3 months. Every deviation from predicted trajectory will be measured. Every spectroscopic signature will be analysed. Every photometric variation will be logged. The Galileo Project observatories, Loeb's privately funded network of sensors designed specifically to look for technological signatures, will be running parallel observations. If something anomalous happens, if mini-probes deploy, if the trajectory changes, if any sign of non-gravitational activity appears, we'll catch it. The window opens in November when 3I-ATLAS emerges from behind the Sun. First observations will come from JUICE on November 4th. Then ground-based telescopes will reacquire it through December. The closest approach to Earth on December 19th will be prime observing time. Then the Jupiter encounter in March with Juno watching. 3 distinct observation windows, 3 chances to characterize this thing definitively. The IAWN activated because those windows matter. Because what we learn in the next 4 months might answer the question that's been hanging over this entire story. Are we alone, or are we being visited? And if we're being visited, what happens next? That's what planetary defense is preparing for. Not an impact, not a rock, a presence. Something intelligent enough to navigate here, patient enough to approach slowly, and capable enough to time its arrival during the one moment we can't watch. The IAWN activation isn't proof of anything except that someone, somewhere, thinks the possibility is real enough to treat seriously. And when the people responsible for preventing extinction-level events decide something warrants that level of attention, the rest of us should probably be paying attention too. Because in 2 days the monitoring begins, in 4 days perihelion hits, and in 3 weeks we start getting answers. The academic war, Wright versus Loeb, and what it means. There's a blog post that went live in July from Jason Wright, an astronomer at Penn State University, and the title is just AVI and 3I-ATLAS. Simple, direct, and it's one of the most brutal academic takedowns I've seen published outside of a peer review rejection. Wright doesn't waste time with pleasantries. He opens by stating flatly that Avi Loeb has gained a reputation for suggesting, and outright claiming, things could be alien spacecraft even when there's little to no objective reason to think so. And then he proceeds to dismantle, point by point, every major anomaly Loeb has been promoting about 3I-ATLAS. This isn't a colleague disagreeing with an interpretation. This is someone calling out what he sees as fundamentally flawed science being pushed directly to the public, while bypassing the normal channels that would catch these errors. Wright's central accusation is that Loeb's analysis contains basic mistakes that any competent planetary scientist would spot immediately. The supposed absence of a coma around 3I-ATLAS, one of the key pieces of evidence Loeb used to argue it might not be a comet, comes from a misunderstanding of how telescope tracking works. When you're photographing a moving object like a comet, you have two choices. You can track the comet, keeping it sharp while background stars trail into streaks, or you can track the stars, keeping them sharp while the comet smears across the frame. Loeb looked at images where the telescope was tracking the comet and saw sharp object without obvious fuzz. Wright points out that of course you don't see a diffuse coma clearly when the exposure is optimized to keep the nucleus sharp. It's not absent, it's just not highlighted in that imaging mode. Different observation strategies, different visual results, same physical object. The size calculations are another point of contention. Loeb has been stating that 3I-ATLAS has a diameter of at least 5 kilometers, possibly larger, making it far more massive than previous interstellar objects. Wright argues that this size estimate comes from assuming the object is an asteroid with low reflectivity, an albedo around 5%. If it's a comet, which spectroscopic data increasingly suggests, then it would have a much smaller nucleus surrounded by a large coma that makes it appear brighter than a bare rock would. The brightness alone doesn't tell you size without knowing composition. It's Astronomy 101. Brightness equals size times reflectivity. You can't solve for one without knowing the other. Loeb picked the assumptions that maximize size and ran with them, but those assumptions aren't justified by the data. Then there's the Mars images from Perseverance rover that went viral in early October. Enhanced versions showed what looked like an elongated cylindrical object, 4 times longer than it was wide, and the internet exploded with claims of a spacecraft. Loeb had to step in and debunk his own community's interpretation. The elongation, he explained, came from the camera stacking hundreds of exposures over 10 minutes, while 3I-ATLAS moved across the sky. Motion blur, not alien engineering. But here's the thing. If the methodology that produces cylindrical spacecraft from motion blur is wrong, and Loeb agrees it is, then why should we trust other methodologies he's using that also make dramatic claims based on imaging artifacts and measurement edge cases? Wright doesn't stop there. He goes after the non-gravitational acceleration claims, the trajectory statistics, even the WOW signal connection. On every point he finds either errors in calculation, unjustified assumptions, or misapplications of statistical reasoning. And he does it in the measured, careful language of someone who's deeply frustrated but trying to stay professional. You can feel the tension in the prose. Here's a direct quote from Wright's blog. Loeb's work and behaviour have been seen as so outrageous in many quarters that it essentially goes unrebutted in popular fora by those who are in the best position to explain what exactly is wrong about it. That's damning. He's saying that planetary scientists, the experts who actually study comets and asteroids for a living, have given up trying to correct Loeb publicly because it's exhausting and thankless, and the public doesn't listen anyway. Stephen Desch from Arizona State has been even more blunt. He called Loeb's work sloppy and accused him of bypassing peer review to feed conspiracy theories directly to the public. That's not abstract criticism. That's an accusation of scientific misconduct. Peer review exists to catch mistakes, to force researchers to justify their methods, to ensure that claims are supported before they reach the media. When you go around that process, when you publish directly to blogs and press releases and interviews, you're making an end run around the quality control that science depends on, and Loeb is absolutely doing that. His Medium blog posts go up before papers are submitted. His interviews make claims that aren't in any published work. He's using his Harvard credentials to give weight to speculations that wouldn't survive formal review. But here's the uncomfortable part. Being wrong about methodology doesn't mean you're wrong about conclusions. Loeb's calculations might be sloppy, his statistics might be questionable, his understanding of cometary imaging might be incomplete. All of that can be true, and 3I-ATLAS can still be anomalous. The academic war between Wright and Loeb isn't really about the object. It's about process, about how science should communicate uncertainty, about the responsibility that comes with public platforms. Wright thinks Loeb is damaging the credibility of the field by making sensational claims on thin evidence. Loeb thinks Wright and others like him are so invested in conventional explanations that they reflexively dismiss anything that challenges the paradigm. And there's a third group watching this fight with interest: the public. The people who aren't astronomers, who don't have access to telescopes or orbital mechanics software, who are trying to figure out what's actually happening based on conflicting expert opinions. When Wright says Loeb is wrong, and Loeb says Wright is closed-minded, what's a reasonable person supposed to conclude? Most people aren't equipped to evaluate the technical arguments. They can't check the math on trajectory statistics or verify spectroscopic calibration procedures, so they fall back on heuristics. Who seems more credible? Who has more to lose by being wrong? Who's motivated by genuine scientific curiosity versus attention-seeking? Loeb's response to his critics has been fascinating and troubling in equal measure. In one recent blog post, he compared himself to a Jewish child prisoner in Theresienstadt concentration camp who drew idealized images of a better world rather than the grim reality of a Nazi jail. He wrote that he and others who dream of a better world than Earth might guide humanity to the promised land by encountering aliens. That comparison, using Holocaust imagery to frame himself as a persecuted visionary, struck a lot of people as wildly inappropriate. It's one thing to say you're being unfairly dismissed like Galileo was. It's another to invoke the systematic murder of 6 million people as an analogy for academic criticism. But it also reveals something about how Loeb sees this moment. He genuinely believes he's on the right side of a historical inflection point, that the scientific establishment is too conservative, too risk-averse, too committed to conventional wisdom, that someone needs to be willing to take reputational hits to push ideas that might be wrong but need to be considered. And maybe he's right about that in the abstract. Science does have a conservatism problem. Paradigm shifts get resisted. Outsider ideas get dismissed too quickly sometimes. The question is whether 3I-ATLAS is actually one of those paradigm-shifting moments, or whether it's a case study in why peer review matters. The betting markets, which are a weird but surprisingly accurate gauge of collective belief, currently put the odds at 75% natural comet, 25% alien technology. Those aren't scientific probabilities, they're aggregated human judgments weighted by confidence and money. But they tell you something about where the discourse has landed. 3/4 of people who care enough to bet think this is a comet. 1/4 think there's something to Loeb's claims. That's not consensus either way. It's deep uncertainty playing out in real time. Chris Lintott from Oxford called Loeb's hypothesis nonsense on stilts. That phrase has history. It comes from Jeremy Bentham, the utilitarian philosopher, who used it to describe natural rights theory. Nonsense on stilts means an idea so absurd that it's elevated beyond mere nonsense into a category of its own. Lintott isn't saying Loeb is mistaken. He's saying the entire framework is misconceived from the ground up, that you can't get to alien spacecraft from the evidence available no matter how you arrange it, that the logical chain is broken at every link, and yet the IAWN activated. NASA is watching. The Galileo project is mobilized. ESA is allocating JUICE observation time. For all the academic pushback, for all the criticism of Loeb's methods, institutions are responding as if the possibility is real. Maybe that's just good practice. Maybe it's risk management. Maybe it's political pressure from people who read headlines and demand action. Or maybe, despite the flawed analysis, despite the methodological problems, there's enough smoke that everyone wants to make absolutely sure there's no fire. Darryl Seligman from Michigan State, one of the lead authors on the paper that first characterized 3I-ATLAS as an interstellar comet, tried to take a middle path. He emphasized that this is only the third such interstellar comet we've ever been able to study, and planetary scientists are super excited to learn about what comets in other solar systems look like. It's a deflection, a way to refocus attention on the legitimate science while stepping around the alien question. But it's also true, even if 3I-ATLAS is completely natural, it's carrying information about planet formation in another star system. The chemistry tells us what volatiles were available in that protoplanetary disk. The trajectory tells us about the dynamics that ejected it. There's real science here that doesn't need speculation about technology to be valuable. The academic war matters because it shapes what happens next. If Loeb's critics win the discourse, If the consensus solidifies around natural explanation, then funding priorities shift. Resources go elsewhere. The urgency drops. 3I-ATLAS becomes an interesting footnote, a weird comet that generated some controversy, and we move on. If Loeb's framing wins, if the technological possibility stays alive in institutional thinking, then we maintain vigilance. We keep watching past the initial observation windows. We design follow-up missions. We take the dark forest hypothesis seriously enough to consider defense scenarios. And that brings us to the thing nobody wants to say out loud but everyone's thinking. What if they're both wrong? What if Wright is correct that Loeb's specific claims are methodologically flawed, and Loeb is correct that something genuinely anomalous is happening? What if the truth is neither natural comet nor alien mothership, but something weirder? Something we don't have a framework for yet? The universe has surprised us before. Pulsars weren't in anyone's theory until we detected them. Exoplanets were speculative until we found thousands. Fast radio bursts came out of nowhere. Science advances by encountering phenomena that don't fit existing boxes and building new boxes to contain them. 3I-ATLAS might be building us a new box whether we want one or not. The academic fight is a sideshow. Wright and Loeb can argue about methodology forever. It doesn't change what the object is. It only changes how we interpret the data we're collecting, and the data is about to get a lot richer. November 4th, JUICE flyby. December 19th, closest approach to Earth. March 16th, Juno encounter. 3 moments when we'll have opportunities to test every hypothesis, conventional and otherwise. The academic war will pause then. Everyone will be looking at the same new data, and we'll see whose framework fits. Until then, we're watching 2 versions of science play out simultaneously. Wright's version, careful and skeptical, demanding extraordinary evidence for extraordinary claims, protecting the field's credibility by pushing back against speculation. And Loeb's version, bold and risky, willing to consider ideas that might be wrong in service of ideas that might be revolutionary, arguing that the cost of false negatives exceeds the cost of false positives when the stakes are first contact. Both are defensible. Both have led to scientific progress in different contexts, and both are about to be tested by an object that doesn't care what either of them thinks. In 4 days, perihelion happens. In 3 weeks, we see what emerged. And all the arguments, all the methodological disputes, all the academic credibility battles will matter less than one simple question. Did the trajectory change? Because if it did, Wright and Loeb can fight about the details later. We'll have bigger problems to solve. First contact protocol when we realize we're not alone. Let me read you something that should terrify you. It's from Avi Loeb's blog, published just 2 weeks ago. As far as I know, there are no protocols for responding to the discovery of functioning alien devices near Earth. The situation is different from detecting radio signals from a source located thousands of light years away. A visitor in our backyard requires immediate attention because it could enter through the front door and pose an imminent threat. Think about that. We have plans for asteroid impacts. We have plans for solar flares. We have plans for pandemics and nuclear war and climate catastrophe. But we don't have a plan for what happens if we confirm that an alien spacecraft is in our solar system right now, close enough to reach Earth within weeks. The Brookings report from 1961 suggested that discovery of extraterrestrial artifacts could cause severe social disruption. It recommended controlled information release, careful management of public reaction, gradual disclosure rather than sudden announcement. That was written when SETI was young, when the idea of detecting alien intelligence was purely theoretical. The protocols they sketched out assumed we'd have time, that we'd receive a radio signal from light years away and could deliberate about how to respond, what to say, whether to reply at all. The protocols assume distance. They assume the thing we're discovering is far enough away that immediate threat is impossible. 3I-ATLAS breaks all those assumptions. If the trajectory changes after perihelion, if we see evidence of non-gravitational acceleration, if mini-probes deploy toward inner-system planets, we'll know within days. Not years, not decades, but days. JUICE makes its flyby on November 4th. Ground-based observatories reacquire the object in early November. By mid-November, trajectory calculations will be refined enough to detect deviations. If something happened during the perihelion blackout, if an Oberth maneuver was executed, we'll see it in the orbital elements. And then what? The first question is who decides what the information means? Not who collects the data, that's straightforward, it's the astronomers operating the telescopes and the spacecraft teams processing telemetry. But who interprets it? Who makes the call that this crosses the threshold from anomalous to artificial? There's no international body with that authority. The IAWN can declare something a potential impact threat, but their mandate doesn't extend to potential contact scenarios. The United Nations has a committee on the peaceful uses of outer space, but they're advisory, not operational. Individual space agencies like NASA or ESA could make determinations, but they'd be national positions, not global consensus. What likely happens is a period of confusion where different groups reach different conclusions at different speeds. The Galileo project, Loeb's privately funded network, would probably be first to claim technological signatures because they're specifically looking for them and have lower evidential bars than institutional science. They'd publish findings, hold press conferences, push the narrative that confirmation has occurred. Mainstream astronomy would be more cautious. They'd want multiple independent measurements, extensive peer review, exhaustive elimination of natural explanations. The gap between those two timelines could be weeks or months. And during that gap, the public would be caught in an information war between confident speculation and careful skepticism. Social media would go insane. That's not hyperbole, it's prediction based on how information spreads now. Every amateur astronomer with a telescope would be posting images. Every conspiracy theorist would be declaring vindication. Every government skeptic would be accusing cover-ups. The signal-to-noise ratio would be catastrophic. And buried in that noise would be the actual data, the real observations, the measurements that matter. Most people wouldn't be able to distinguish between them. They'd pick narratives based on prior beliefs, on who they trust, on what fits their worldview. And by the time scientific consensus formed, if it ever did, public opinion would already be locked in. Governments would face impossible choices. Do you get ahead of the story and make an official statement before scientific consensus? Do you risk being wrong? Risk inciting panic over something that turns out to be natural? Or do you wait, maintain silence, let the rumours build, and risk looking like you're hiding information? Both paths have historical precedent, and both have gone badly. The War of the Worlds radio broadcast in 1938 caused panic, despite being obvious fiction, because people tuned in late and missed the disclaimer. The Orson Welles effect is real. But government silence during genuine crises, from pandemic responses to intelligence failures, breeds conspiracy theories that are often more damaging than the truth would have been. Let's say the confirmation comes. Let's say by mid-November the evidence is strong enough that major space agencies issue coordinated statements, acknowledging that 3I-ATLAS shows characteristics inconsistent with natural objects. What happens in the first 24 hours? Markets would crash. That's almost certain. Not because of rational assessment of economic impact, but because uncertainty kills markets faster than bad news does. Investors would flee to safety. Governments would halt trading to prevent complete collapse. Emergency economic measures would deploy within hours. Religious institutions would face existential questions. The Catholic Church has actually been preparing for this. Vatican astronomers have publicly stated that the existence of extraterrestrial intelligence wouldn't contradict Catholic theology, that God's creation could extend beyond Earth, that aliens could have their own covenant with the divine. Other denominations are less prepared. Evangelical Christianity, particularly American evangelical Christianity, has significant theological commitments to human uniqueness, to Earth's special status in creation. Confirmation of aliens doesn't just challenge those beliefs, it potentially invalidates them. You'd see schisms, rapid reinterpretations, or in some cases outright denial. The psychological impact would vary wildly by cultural context. Western secular cultures might adapt relatively quickly. The idea of aliens is already normalized in fiction, in entertainment, in speculative science. It would be shocking but not incomprehensible. Other cultures, particularly those where religious cosmology is tightly integrated with daily life, would face harder adjustments. And then there are the accelerationists, the people who would see first contact as an opportunity, a chance to leapfrog current limitations, to access advanced technology, to solve Earth's problems with alien help. They'd be pushing for engagement, for communication attempts, for welcoming gestures. And they'd be opposed by those who see any contact as inherently dangerous, who want isolation, who think humanity's only chance is to hide and hope we're beneath notice. Military responses would activate immediately, not because anyone thinks we can fight an interstellar civilization, but because that's what militaries do. They prepare for threat scenarios no matter how asymmetric. Space Force, which most people forgot exists, would suddenly be the most important branch of the US military. Defense satellites would be tasked with tracking. Ground-based radar networks would go to high alert. Missile defense systems, which are designed for ballistic threats but could theoretically intercept slow-moving objects in near-Earth space, would be positioned. It would all be futile if the technology gap is what we expect, but the preparations would happen anyway because doing nothing isn't politically viable. Then there's the communication question. Do we try to send messages? If 3I-ATLAS deployed mini-probes toward Earth, and those probes arrive in late November or early December, do we attempt first contact protocols? Radio signals, laser communications, mathematical sequences, prime numbers, the kinds of things SETI has been planning for decades? The problem is that those protocols assume cooperative contact, assume the other side wants to communicate. If the dark forest hypothesis is correct, if this is surveillance or reconnaissance preceding something hostile, then announcing our presence more clearly than it already is would be suicidal. But how do you tell the difference between a probe sent to observe and a probe sent to evaluate us for destruction? You can't. Not without more data, not without some kind of interaction, and by the time you have that data, it might be too late to change strategy. Loeb compared this to a blind date where you hope the other person is friendly, but have to worry about serial killers. It's a deliberately provocative analogy, but it captures the uncertainty. When you don't know intentions, when you can't even be sure what the other party's capable of, every decision is a gamble. Do you approach or retreat? Do you show strength or vulnerability? Do you try to appear valuable as potential allies, or do you try to appear threatening enough that conquest isn't worth the cost? Game theory offers frameworks, but they all depend on assumptions about the other player's utility function, and we have no basis for those assumptions. Academic institutions would scramble to stay relevant. Every university with an astronomy department would be launching research initiatives, applying for emergency grants, holding symposia. The field of astrobiology, which has been relatively niche, would explode. Linguists would propose xenolinguistics programs despite having zero examples to work from. Philosophers would debate the moral status of alien intelligence, whether we have obligations toward them, whether they have rights under human frameworks. It would be an intellectual gold rush, everyone trying to stake claims in a field that didn't meaningfully exist a week earlier. The technology question would dominate practical discussions. If this is a spacecraft, if it's capable of interstellar travel, then it has power systems, propulsion systems, materials science, and computing that dwarf anything we've achieved. Does reverse engineering become the priority? Do we try to recover pieces, study the probes if they land or crash? Or is the technology gap so vast that attempting to understand it would be like showing a smartphone to someone from the Bronze Age? They could recognize it as sophisticated, even figure out it does things, but the underlying principles, the physics and engineering, would be completely opaque. We might be in the same position. And then there's the colony question that nobody wants to voice. If 3I-ATLAS is artificial, if it's a mothership, how many are there? Is this a unique probe from one civilization exploring randomly? Or is it part of a network, a regular survey route, one of thousands or millions of similar objects scattered across the galaxy? If it's the latter, then we're not facing first contact, we're realizing we've always been in a populated neighborhood and just never noticed. That changes everything about how we think about our future, about expansion into space, about what's possible and what's permitted. If the galaxy is already claimed, already divided, already governed by powers vastly older than us, then humanity's cosmic destiny might be a lot more constrained than we imagined. The hope scenario is benevolence. That contact brings technology transfer, medical advances, solutions to climate change and energy scarcity, answers to fundamental physics questions we've been stuck on. That the reason aliens would visit is curiosity, scientific interest, maybe even a kind of cosmic altruism, where advanced civilizations help younger ones navigate the dangerous period between technological capability and wisdom. The Drake equation suggests intelligent life is rare. If you beat the odds to develop, maybe there's a responsibility to help others do the same. That's optimistic. It's also completely unsupported by evidence. We have one example of intelligent life, us. and we're not particularly altruistic to other species on our own planet. The fear scenario is resource extraction. Not our resources exactly, but the sun's energy, the asteroid belt's metals, the real estate. Earth might be valuable or it might be in the way. Terraforming takes centuries, but if you're patient and crossing interstellar distances, you're already thinking in those time frames. A probe assessing habitability, evaluating what's here, cataloguing defences, that's what you'd send before committing to a campaign. And if the assessment is that the locals are primitive, fragmented, barely spacefaring, incapable of meaningful resistance, then the report goes back and the fleet comes forward. That's the nightmare. That we're not encountering exploration, we're encountering the advanced scouts of colonization, and we won't know which until it's far too late to change the outcome. These aren't theoretical exercises anymore. If November brings confirmation, these questions become immediately practical. Every government, every institution, every person with power or platform will need positions on communication, defense, disclosure, preparation. And we have 4 days to hope we never need to answer them, or 4 days to start getting ready for the biggest transition in human history. Because if it's real, if 3I-ATLAS is artificial, then everything after is measured in before contact and after contact. And we're living in the last moments of before, counting down to a perihelion that might change what it means to be human in this universe. The mothership hypothesis, what could deploy during perihelion. There's a calculation in the Hibbard, Crowell and Loeb paper that most people skimmed past because it's buried in technical trajectory analysis, but it's the one that should keep you awake. If 3I-ATLAS is a mothership, if it's carrying smaller spacecraft designed for inner system exploration, then the optimal deployment window is perihelion. And the optimal arrival window for those probes to reach Earth is late November to early December 2025. Not years from now, not decades. 6 to 8 weeks from today. The delta V requirements are surprisingly low. Less than 5 kilometers per second to reach Earth from 3I-ATLAS's trajectory if the burn happens at perihelion. That's the speed of an intercontinental ballistic missile. We've had that technology since the 1960s. If they're capable of interstellar travel, they can manage 5 kilometers per second. Let's think about what these mini probes might actually be. Not in science fiction terms, not starships with crew and weapons, but in practical reconnaissance terms. Small, probably autonomous, heavily shielded against radiation, with just enough propulsion to make trajectory corrections and enough sensors to gather data. Maybe the size of a car, maybe smaller. Mass budgets for interstellar travel are brutal. Every kilogram costs exponentially in fuel or time or both. You don't send bulk. You send the minimum viable payload that can accomplish the mission. For reconnaissance, that's instruments and computers, and enough fuel for local maneuvering. Humans, if there are humans or equivalent, stay on the mothership. The probes go ahead. The paper calculates that if 3I-ATLAS wanted to intercept Earth, the arrival date that minimizes delta V falls in the late November window. Specifically, late November to early December. That's not arbitrary, it's orbital mechanics. The positions of Earth and 3I-ATLAS after perihelion, the phase angles, the relative velocities, all conspire to make that window optimal. Before that, you need more fuel. After that, you need more fuel. There's a sweet spot and it opens in about 5 weeks. If probes deployed on October 29th, if they fired engines to brake and redirect toward Earth, they'd arrive right in that window. We wouldn't see them coming. Objects that small, not emitting light, just coasting on ballistic trajectories with occasional corrections, would be invisible to our detection networks until they were very close. Maybe hours away, maybe less. What would they do? The benign scenario is observation. Fly by Earth, scan the planet, measure atmospheric composition, map surface features, catalogue electromagnetic emissions, detect the signatures of industrial civilization. Is what we'd do if we sent probes to another inhabited world. You gather data before making decisions about further contact. You assess technological level, social organization, potential threats, potential cooperation opportunities. Voyager carried a golden record with sounds and images of Earth. A message in a bottle for anyone who might find it. That's what benign reconnaissance looks like. Curiosity expressed through instrumentation. The concerning scenario is different. Same instruments, same data collection, but the purpose isn't scientific, it's strategic. You map infrastructure, identify critical nodes, catalogue defenses, measure response capabilities. You figure out where the power grids are, where the communication hubs sit, where the military installations cluster. Not because you plan to use that information immediately, but because if you ever need to use it, you want the assessment already done. This is what spy satellites do, what reconnaissance drones do, what intelligence gathering looks like when you're preparing for contingencies. And the data collected for benign purposes looks identical to data collected for strategic purposes. You can't tell the difference from methodology, only from what happens afterward. There's a third scenario that's weirder. The probes aren't here to observe us at all. They're here to observe something else, and we're incidental. Maybe Earth's biosphere is the target, not human civilization. Maybe there's ongoing monitoring of how life develops on worlds, and we're just one data point in a long-term study. Maybe the probes visit periodically, have been visiting for thousands or millions of years, and we're only now technologically sophisticated enough to notice them. That would make us late to our own discovery, realizing we've been watched long after the watching began. It's humbling and disturbing in equal measure. The paper mentions that 3I-ATLAS could release probes toward multiple targets. Mars got a close flyby in October, within 190 million kilometers. Venus will get one in the coming months. Jupiter is on the trajectory for a March encounter. If the goal is to survey the solar system, hit all the major bodies of interest, this path does that efficiently. You're not optimizing for one planet, you're optimizing for coverage. And from a strategic standpoint, that makes sense. Why come all this way to study one world when you can study several? The infrastructure cost of interstellar travel is so enormous that once you're here, the marginal costs of additional observations are trivial. You send probes everywhere you can reach. Now let's talk about what happens if probes arrive at Earth and we detect them. Not after they land or crash, but while they're inbound, while we have hours or days of warning. Do we try to intercept? The technical capability exists. We have missiles that can reach low Earth orbit. We have anti-satellite weapons that could theoretically hit something on approach if we knew the trajectory precisely enough. But should we? If these are reconnaissance probes from a civilization capable of interstellar travel, destroying them might be interpreted as an act of war. It might be the worst decision humanity ever makes, taking a first contact scenario and turning it into a conflict scenario because we reacted defensively to something that wasn't actually a threat. On the other hand, allowing unknown objects to enter our airspace, our orbital space, unchallenged sets a precedent of passivity. It signals that we can't or won't defend ourselves. Game theory suggests that showing capability, even if you don't use it, affects how others perceive and treat you. A civilization that can intercept probes is different from one that can't, even if the interception would ultimately be futile against a more advanced adversary. The demonstration matters. But these are decisions that would need to be made in hours, under uncertainty, by people who aren't prepared for the question. And the cost of getting it wrong is unbounded. The communication question comes up again here. If probes arrive, do we send messages? Radio broadcasts, laser signals, mathematical sequences, attempts at establishing protocols? The arguments for are obvious. It's what SETI has been preparing for. It's the first step in any contact scenario. The arguments against are dark forest. If they don't know we're here yet or aren't sure we're worth noticing, broadcasting our presence might be the last mistake we make. But if they sent probes specifically to Earth, they already know. The choice to broadcast wouldn't be revealing ourselves. We're already revealed. It would be attempting to shape the nature of the interaction from the start, trying to establish that we're cooperative, communicative, interested in peaceful contact. Whether that helps or hurts depends entirely on their intentions, which we have no way to assess. There's an engineering detail worth considering: the power requirements for these mini-probes. If they're using chemical propulsion, traditional rockets, they need fuel mass comparable to payload mass for the delta-V required. That makes them bigger, heavier, harder to deploy in large numbers. If they're using something more advanced, nuclear thermal, ion drives, fusion, maybe even something we don't have physics for yet, the mass ratios improve dramatically. You can make them smaller, lighter, carry more of them. The fact that 3I-ATLAS is massive, at least 33 billion tons based on trajectory analysis, means it could be carrying hundreds or thousands of small probes and barely notice the mass budget. A mothership doesn't need to land. It doesn't need to enter atmosphere. It just needs to carry the things that do, and release them at the right moments. Loeb's blog post from October 22nd describes this exact scenario. If 3I-ATLAS is a massive mothership, it will likely continue along its original gravitational path and ultimately exit the solar system. In that case, the Olbers maneuver might apply to the mini-probes it releases at perihelion towards solar system planets. That's the move that makes strategic sense. The mothership stays safe, stays on a departure trajectory, doesn't commit to staying bound in a system where it could theoretically be trapped or targeted. The probes take the risks, gather the data, and if they're lost or destroyed, it's acceptable losses. The mothership can report back regardless. Where would probes land if they're designed for surface exploration? Probably not cities. Too much risk of immediate detection and confrontation. Remote areas. Regions with minimal human presence, where they can operate without interference while still being able to observe from distance. High elevation sites offer good sightlines for observation. Desert regions have minimal weather interference and stable ground for instrumentation. Polar areas are isolated but scientifically interesting if you're studying climate. The ocean floors are another option, vast and largely unmonitored, perfect for hiding while deploying sensors. We wouldn't find them unless we were specifically looking, and even then the search space is absurdly large. Or maybe they don't land at all. Maybe they stay in orbit high enough to avoid atmospheric drag, low enough for detailed observation. Geostationary orbit is crowded with our satellites, but there's room. Lower orbits are harder to maintain without fuel for maneuvering, but offer better resolution. A probe network distributed across multiple orbital planes could achieve total Earth coverage with relatively few assets, and if they're stealthy, if they're not emitting, not reflecting much light, not making themselves obvious, we might never spot them among the thousands of pieces of space debris and defunct satellites already up there. The timeline matters. If deployment happened at perihelion on October 29th, and transit time to Earth is 4 to 6 weeks, then arrival happens in early December. Right around December 19th, which is also when 3I-ATLAS makes its closest approach to Earth at 1.8 astronomical units. That's not coincidence, that's planning. The mothership passes at safe distance while the probes arrive at the target. You get simultaneous observation from 2 vantage points, the close-in probes providing detailed data, the distant mothership providing context and communication relay. It's elegant mission design if you're coordinating reconnaissance across interplanetary distances. What could we do to detect inbound probes? Not much with current infrastructure. Our space surveillance network is designed to track objects in Earth orbit, and maybe cislunar space. Things approaching from interplanetary space, small objects without active transponders, would only be visible when very close, maybe inside the orbit of the Moon. By then you have hours at most to respond. Upgrading detection capabilities, deploying new sensors, establishing better coverage, all of that takes months or years. If the probes are arriving in December, we won't be ready. We'll find out about them the same way we find out about most things, when they're already here and someone notices something strange. The psychological impact of confirmed probe arrival would be different from mothership detection. The mothership is distant, abstract, not an immediate presence. Probes in orbit or on the surface are visceral, they're here, they're close, they're potentially watching you specifically. The paranoia factor would be extreme. Every unusual phenomenon gets interpreted as probe activity. Every unexplained light in the sky, every weird electromagnetic signal, every odd satellite behaviour becomes evidence or potential evidence. The conspiracy theories that have bubbled around UFOs for decades suddenly have concrete focus, and some of them might be right, which makes sorting signal from noise nearly impossible. We need to consider the scenario where nothing happens, where perihelion passes, November comes, observations show normal cometary behaviour, no trajectory changes, no probe deployment, no anomalies beyond the ones already catalogued. Does that mean the technological hypothesis was wrong? Or does it mean the technology is better than we thought, capable of manoeuvres we can't detect, operating on timelines longer than our attention span? If the mothership parks in Jupiter orbit in March, settles into a stable position around the largest planet in our system, out of the way but present, that's not an immediate threat, but it's a permanent change. We'd have to live with knowing something artificial is out there, watching, waiting, doing whatever it's designed to do, and we might never know more than that. The uncertainty could persist for years, decades, generations. No contact, no communication, just presence. just the knowledge that we're observed. That might be worse than contact. At least with contact you get answers. With observation you get questions that multiply without resolution, and the questions shape behaviour. Do we change how we act knowing we're watched? Do we try to impress, to show our best qualities? Or do we ignore it, live as we would anyway, refuse to perform for unknown judges? These aren't abstract philosophical questions if probes arrive. They're practical considerations about how to be human under alien observation, and we've got 5 weeks to find out if we need answers. Why now? What makes 2025 special? If 3I-ATLAS is artificial, if it's carrying intelligence or acting on behalf of intelligence, then the question that haunts me isn't whether it's here, it's why now. Interstellar travel takes time, even moving at 68 kilometers per second, which is what 3I-ATLAS is doing at perihelion. You're looking at tens of thousands of years to cross between neighbouring star systems. Hundreds of thousands if you're coming from farther out. The planning horizon for an interstellar mission is geological. You don't launch something like this on impulse. You launch it because you have reason to believe the destination will be worth the investment when it arrives. So what changed about Earth, about humanity, about this moment in our development that would make us interesting now? There's a concept in astrobiology called the technosignature window. It's the period during which a civilization is detectable from interstellar distances. Before industrial technology, Earth looked like any other habitable world. Lots of oxygen in the atmosphere from photosynthesis, liquid water, temperature in the right range, but nothing that screamed intelligence. We had cities, agriculture, complex societies, but from light years away those don't show up in spectroscopy. What shows up is chlorophyll, methane from biology, signs of life but not necessarily intelligent life. That was Earth for billions of years. Then something changed. 1876, if you want a specific date, when Alexander Graham Bell patented the telephone. Not because the telephone itself matters to alien detection, but because it marked the beginning of telecommunications, which led to radio, which led to broadcast signals propagating into space at light speed. Suddenly Earth wasn't just alive, it was noisy. Radio transmissions, television broadcasts, radar pulses, all of it leaking into space, creating an expanding bubble of electromagnetic signals with Earth at the centre. That bubble is now about 150 light-years in radius. Any civilization within that radius with sensitive enough receivers could detect us. They'd know something technological is happening here, but radio is just one signature. There are others that appeared even more recently. Nuclear weapons testing in the 1940s and 50s created atmospheric signatures, isotope ratios that don't occur naturally in the concentrations we produced. The tests were loud, energetically. Multiple kiloton and megaton detonations pumping gamma rays and neutrons into the atmosphere, briefly making Earth one of the brightest objects in the solar system in certain wavelengths. If you were watching, if you had the right instruments pointed this way, you'd see a planet that just figured out nuclear fission and was testing it in open air. That's a technosignature. That's a development marker. Then there's artificial light. Satellite imagery from the 1980s onward shows Earth's night side blazing with cities, billions of lights outlining coastlines and continents. From space, from even nearby space like the moon, it's obvious. From interstellar distances with good enough telescopes it would still be detectable. The light pollution we consider a problem is also a beacon. It says this world has dense populations using significant energy at night, which implies electricity generation, infrastructure, urbanization, all markers of technological civilization. The atmospheric composition changed too. Carbon dioxide levels rose sharply starting in the Industrial Revolution, but the acceleration in recent decades is unprecedented in geological records. Methane increased, nitrogen oxides increased. CFCs appeared where they'd never existed naturally. From a distance, analysing light passing through Earth's atmosphere during transits, if you had the right viewing angle, you'd see chemical fingerprints of industrial activity. Not just life, but technology at scale. That signature has only been strong for about 70 years. Before that, Earth's atmosphere looked pre-industrial. So if you're mapping the galaxy, cataloguing which worlds might develop spacefaring civilizations, Earth only became obviously technological in living memory. The signals announcing our presence have been propagating outward for roughly a century, reaching farther every year. If 3I-ATLAS was launched in response to detecting those signals, If some civilization noticed our radio bubble, or our nuclear testing, or our atmospheric changes and decided to investigate, the timing fits. Launch a probe a century ago, cruise for decades, arrive now, when the civilization that sent the signals is hopefully still around, and possibly developed enough to be interesting. But there's another possibility that's darker. Maybe they're not responding to our signals. Maybe they're on a regular survey route, visiting habitable worlds periodically to check status. Earth gets visited every 100,000 years, every million years, some interval long enough that evolution can produce changes between visits. Most visits, nothing interesting is happening. Life exists but hasn't reached complexity or intelligence. Then they arrive in 2025 and surprise, the apes figured out nuclear fission and spaceflight. That makes this visit different from previous ones. Not because they chose now, but because we happened to develop during their scheduled survey window. We're incidental to their timing, and they're responding to what they find rather than what they expected. There's a third scenario based on the Great Filter concept, the idea that somewhere between single-celled life and galaxy-spanning civilization, there's a barrier that most species don't cross. Maybe it's developing multicellular organization, maybe it's achieving technological intelligence, maybe it's surviving the period where you have weapons of mass destruction, but not the wisdom to avoid using them. That last one is where we are now. Nuclear weapons, biological weapons, climate alteration, AI development, synthetic biology. We've reached the point where we can destroy ourselves, or fundamentally alter our trajectory, and we're doing it faster than our social institutions can adapt. If you're an advanced civilization monitoring developing worlds, the Great Filter period is when you'd pay attention. Before that, the species isn't interesting because they'll probably die in some natural catastrophe. After that, if they survive, they're potential peers or at least potential participants in whatever galactic community exists. But during the filter, during the narrow window where they could go either way, that's when intervention might matter. Or when assessment becomes critical. Are these beings about to destroy themselves? Are they going to stabilize? Do they need help or a warning or just observation to see what happens? We're in that window now. We've been in it since 1945 when Trinity tests proved we could split atoms. And we might exit it in the next century one way or another. China landing on the far side of the moon, SpaceX developing reusable rockets, James Webb Telescope coming online, CRISPR editing human genomes, large language models achieving apparent reasoning. These are all developments in the last decade. The pace of change is exponential. If you were watching from outside and you saw a species go from first powered flight to landing on their moon in 66 years, saw them go from room-sized computers to pocket supercomputers in 50 years, you'd recognize the pattern. This is a civilization in rapid development phase. They're unstable, unpredictable, but they're also potentially about to become much more capable. That makes now interesting in ways that a century ago or a century from now might not be. There's also the possibility that it's not about us at all, it's about Earth's position in a larger pattern. The solar system is moving through the galaxy. We orbit the galactic centre once every 230 million years or so. We're currently in a region called the Orion Spur, a minor arm between major spiral arms. Different regions of the galaxy have different stellar densities, different metallicities, different amounts of dust and gas. Maybe 3I-ATLAS is surveying this region, visiting multiple systems, and Earth is one stop on a much longer route. We happen to be the inhabited one, which makes us more interesting than the gas giants and dead rocks. But we're not the reason for the mission, we're a discovery during the mission. The WOW signal connection adds another layer. That signal was detected in 1977 from the direction of Sagittarius. 3I-ATLAS is arriving from within 9 degrees of that same direction. If the two are related, if the signal was sent by whoever launched 3I-ATLAS, or sent by 3I-ATLAS itself while still far out, then the timing tells a story. Signal sent in 1977, reaches Earth, gets detected but not understood. 48 years later, the object that sent it arrives. That's a reasonable timeline for a probe travelling at a fraction of light speed. Not fast by science fiction standards, but fast enough. And it means the signal might have been a warning, an announcement, a test to see if we'd respond. Anything. We didn't respond, we just logged it as unexplained and moved on. Maybe that told them something about our readiness for contact. Artificial intelligence development might be the key factor. Not because AI is inherently dangerous, though it might be, but because it represents a threshold. Once you have artificial general intelligence, once you have systems that can improve themselves, design better versions recursively, you're potentially months or years away from superintelligence. And superintelligence changes everything. It solves problems humans can't solve, designs technologies humans can't design, operates at speeds and scales beyond biological cognition. If you're an alien civilization monitoring for danger signals, watching for species that might become threats or need intervention, AI development is the red flag. It means the species is about to change fundamentally, and you need to assess them before that change happens, because after, you might be dealing with something completely different. We announced our AI capabilities pretty loudly. Research papers, public demonstrations, commercial deployments, all of it visible in telecommunications that leak into space. If someone was listening, they'd know we're working on this. They'd know we're close. And if their own history includes AI development, if they went through this transition and know what it entails, they might have strong opinions about how we should or shouldn't proceed. That could motivate a visit now rather than later, before we reach a point where intervention becomes harder or riskier. Climate change is another marker. Terraforming in reverse, basically. We're taking a habitable planet and making it less habitable through industrial activity. From outside, that looks like either ignorance or self-destruction, and either way it suggests a species that hasn't figured out planetary management. If you're evaluating whether a civilization is stable enough to expand beyond their homeworld, watching them destabilize their own environment is a bad sign. It suggests they'll repeat the same mistakes elsewhere, that giving them access to other worlds or other systems might just spread the problem. Or alternatively, it suggests they're about to face a crisis that will either kill them or force rapid adaptation, and the outcome of that crisis determines what kind of neighbours they'll be. The pandemic is recent enough to matter too. 2019 to 2023, global disruption from a respiratory virus. Our response was chaotic, politicised, uncoordinated across national boundaries. Some countries did well, others failed catastrophically. If you're assessing human civilization's ability to handle existential threats, the pandemic is a live fire exercise, and we got mixed grades. We developed vaccines faster than ever before in history, that's impressive. But we also had significant populations refusing those vaccines based on conspiracy theories, governments prioritizing economic activity over public health, international competition over cooperation. From outside, that looks like a species that has the tools to save itself but might not use them effectively. That's diagnostically useful if you're trying to predict our future trajectory. So why now could be answered a dozen ways. Because we became detectable, because we're in the great filter window, because we're developing AI, because we're destabilizing our climate, because we had a pandemic that revealed our coordination failures, because we're in a particular region of the galaxy at a particular time, because regular survey schedules put a probe here during our technological emergence, or because something we haven't considered, something that seems normal to us but is significant to them, triggered attention. The thing about unknown intelligences is you can't predict what they'll find important. They might care about things we think are trivial and ignore things we think are critical, but if I had to choose, if I had to pick the most likely reason why an alien probe would visit Earth in 2025 specifically, I'd say it's the conjunction of capabilities and vulnerabilities. We're capable enough to be interesting. We have spaceflight and nuclear technology and sophisticated computing. But we're vulnerable enough to be manageable. We're confined to one planet. We're politically fragmented. Our weapons are powerful but not existential at interstellar scales. We're at peak observability, where we're obvious from a distance but not yet sophisticated enough to hide or defend effectively. That window might be narrow, maybe a few centuries between becoming detectable and becoming either extinct or too advanced to approach casually. If you want to study or contact or assess a developing civilization, you do it during that window. And for us that window is now. We're loud, we're visible, we're changing rapidly, and we're not going anywhere soon. That makes us a perfect target for reconnaissance. And if 3I-ATLAS is reconnaissance, if those probes are coming, then the assessment is already underway. They're not asking why now, they're recording what now looks like. And we're performing for judges we can't see, being evaluated by standards we don't know, with consequences we can't predict. That's what makes 2025 special. Not because we chose this year for anything, but because this is the year we became worth the trip. The dark forest, when silence means danger. There's a passage in Liu Cixin's science fiction novel The Three-Body Problem that changed how a lot of people think about alien contact. It's called the dark forest theory, and it goes like this. The universe is a dark forest. Every civilization is an armed hunter stalking through the trees, trying to be as quiet as possible, because everyone else is also armed, also hunting, and the first one to make noise gets eliminated. In this framework, the reason we haven't detected alien civilizations isn't because they're rare. It's because the successful ones stay hidden. They know that announcing your presence, revealing your location, broadcasting your capabilities is suicidal. Because somewhere in the dark forest someone stronger is listening, and they eliminate potential threats before those threats can grow. It's a bleak worldview. It assumes that cooperation between civilizations is impossible, or at least so risky that silence is the dominant strategy. And it offers an explanation for the Fermi paradox, the question of why we see no evidence of aliens despite the universe being old enough and large enough that we should. According to dark forest thinking, we see no evidence because all the civilizations that made themselves visible got destroyed. The ones that survived learned to hide, learned to listen without transmitting, learned to eliminate others before being eliminated themselves. It's cosmic game theory taken to its logical and horrifying endpoint. Now apply that framework to 3I-ATLAS. If the dark forest theory is accurate, if the galaxy operates on those principles, then an interstellar object approaching our solar system isn't exploration, it's reconnaissance preceding extermination. You don't visit another civilization out of curiosity, you visit them to assess whether they're a threat. And if they are, or if they might become one, you eliminate the threat while it's manageable. That's the logic Loeb referenced when he mentioned the dark forest in his paper with Hibbard and Crowell. They weren't endorsing the theory exactly, but they were acknowledging it as a possibility that needs to be taken seriously if we're considering artificial origins for 3I-ATLAS. The strategic logic is coldly rational. If you're a spacefaring civilization, and you detect another civilization developing in your region of the galaxy, you face a decision tree. Option 1. Ignore them. Hope they stay confined to their home system. Assume they're not a threat. That's risky because civilizations develop unpredictably. The ones that seem primitive now might leapfrog technologically, might expand rapidly, might become competitors or threats in timeframes shorter than you expect. Option 2. Contact them, attempt cooperation, establish communication, and mutual benefit. That's the optimistic path, but it requires trust. You're revealing yourself, your location, your capabilities. If they're hostile or become hostile later, you've given them targeting information. Option 3 is the dark forest option. Strike preemptively while they're vulnerable. You don't wait for them to become spacefaring. You don't wait for them to develop weapons that might threaten you. You hit them while they're confined to one planet, while their technology is primitive, while they can't meaningfully resist. It's not genocide for its own sake. It's preventive security. You're eliminating a potential future threat before it materializes, and from certain game theoretic perspectives it's the optimal strategy. If the costs of being wrong about another civilization's intentions are existential, you can't afford to be wrong. Better to eliminate 1,000 harmless civilizations than let one dangerous one develop. That logic is monstrous by human moral standards. We'd call it paranoid, evil, unjustifiable. But human moral standards evolved in an environment where the worst-case scenario was tribal conflict, maybe regional war, events that were terrible but not extinction level. Our ethics aren't optimized for situations where a single mistake eliminates your entire species. And if you're a civilization that's survived for millions of years, you've probably encountered situations that taught you the cost of being too trusting, too slow to act, too moral by standards that get you killed. Natural selection applies to civilizations too. The ones with survival strategies that work are the ones still around, and if preemptive elimination works better than trust, then the civilizations we'd encounter are the ones that learned that lesson. So what does a preemptive strike look like against a planet? You probably don't want kinetic weapons, giant rocks accelerated to relativistic speeds that sterilize the surface. That's wasteful. It destroys infrastructure, ruins habitability, makes the planet useless to you afterward. You want something cleaner. Biological weapons are options. Designer pathogens that target the dominant species without harming the ecosystem broadly. Release them from orbit, let them spread, wait for the population to collapse. Then you move in and claim a habitable world without the mess of bombardment. Or you use nanotech, self-replicating machines that disassemble the threat at molecular level. Harder to defend against because they're everywhere at once and conventional weapons don't touch them. Or you don't destroy the species, you just cripple them permanently. Take out their satellites, their power infrastructure, their communications. Reduce them back to pre-industrial capability. They're no longer a threat because they can't reach space, can't threaten you, can't do anything except survive on their devastated world. And maybe you leave monitoring systems to make sure they never climb back up. It's a prison planet scenario. The civilization stays alive but neutered, locked in technological stasis while you control the high ground. That's arguably more humane than extinction, but it's still the end of any meaningful future for that species. The question is whether you'd announce yourself before striking or just hit without warning. Announcing has strategic downsides. It gives the target time to prepare, time to respond, time to possibly get lucky and hurt you before you finish them. But it also has benefits. If you're not certain about threat level, if you want to assess capability and intent before committing to elimination, you might send a probe first. See how they react to its presence. Do they try to communicate? Do they try to destroy it? Do they ignore it? The response tells you what you're dealing with and helps calibrate your next move. 3I-ATLAS, if it's a probe, might be that assessment. It approaches in a way that's detectable but not overtly threatening. It doesn't accelerate toward us, doesn't send clear signals, just moves through the system on a trajectory that brings it close to major bodies. If we ignore it, that tells them we're either oblivious or uninterested. If we observe but don't interfere, that suggests we're aware but passive or cautious. If we attempt to intercept or destroy it, that tells them we're aggressive, we perceive threats. We're willing to act kinetically against unknown objects. Each response pattern provides data about our nature, our capabilities, our threat level. And based on that data, decisions get made about what happens next. Loeb's comparison to a blind date where you worry about serial killers is apt. When you don't know the other party, when you can't predict their intentions, you watch for warning signs. And from an alien perspective, humanity has a lot of warning signs. We're aggressive to each other, wars are constant, our history is soaked in blood. We're aggressive to other species, we've driven countless to extinction. We exploit and destroy ecosystems for short-term gain. We develop and deploy weapons of mass destruction. We tested nuclear weapons hundreds of times, knowing the fallout was harmful. We're unstable politically, fragmented into competing nations that can't coordinate even on existential threats like climate change or pandemics. If you're assessing whether this species will be a responsible galactic neighbour, the evidence doesn't look good. But there's counter-evidence too. We create art, music, literature, beauty for its own sake. We have individuals and groups dedicated to preservation, conservation, peace. We've established international laws and norms that sometimes actually work. We went to the moon and left plaques saying we came in peace for all mankind. We sent Voyager with golden records trying to communicate with whoever might find them. We're contradictory, yes, but that contradiction includes genuine impulses toward cooperation and exploration rather than conquest. Whether that's enough to offset the warning signs is the assessment question. The Dark Forest scenario is terrifying because there's no good defense. If a civilization millions of years ahead of us decides we're a threat, we can't stop them. Every weapon we have, every defense we could mount, is irrelevant against technology that far advanced. It would be like Bronze Age humans trying to fight modern military. The disparity is so vast that resistance is meaningless. Our only hope in that scenario is that we're wrong about their intentions, that the Dark Forest logic doesn't apply, that they're benevolent or at least indifferent rather than preemptively hostile. But hope isn't a strategy. If you're planning for worst case, if you're trying to think through what humanity should do if 3I-ATLAS represents that kind of threat, you face the reality that there's nothing effective we can do. You could argue for trying to hide, shutting down broadcasts, stopping electromagnetic emissions, going dark in hopes they don't notice us or conclude we're not worth the effort. But we've been broadcasting for a century. The signals are already out there, already propagating. You can't recall them. And even if we went silent today, our artificial lights are visible. Our atmospheric composition is altered. The signs of industrial civilization persist. We can't hide what we've already announced. The only thing going dark accomplishes is making ourselves vulnerable to any other observers who see us stop transmitting and wonder what happened, whether we collapsed or went into some kind of stealth mode that suggests hostile intent. You could argue for accelerating space development, getting off Earth, establishing colonies on Mars and the Moon and asteroids, distributing the species so we're not all on one vulnerable world. That's good strategy for long-term survival anyway, but it takes decades, maybe centuries to establish self-sufficient off-world populations. If 3I-ATLAS represents an immediate threat, if probes are arriving in December, we don't have that timeline. We'd be like ants building new hills while someone's already got the magnifying glass focused. You could argue for attempting communication, trying to demonstrate that we're not threats, that we're worth preserving, that we have value beyond just being eliminated. But what do you say? How do you prove you're peaceful when your entire history suggests otherwise? How do you promise you won't be a future threat when you don't know what your future holds, when your own development trajectory is unstable? Communication might help, might establish dialogue, might create space for negotiation, or it might just confirm what they already suspected, that we're self-aware enough to be dangerous, communicative enough to potentially coordinate with others, and therefore something that needs to be handled. The bleakest version of dark forest logic is that by the time you're asking these questions, it's already too late. The reconnaissance happened years ago, decades ago. The decision was made before you knew you were being evaluated, and the strike is already inbound. You're not negotiating your survival, you're waiting for an execution that's already been ordered. 3I-ATLAS reaches perihelion, deploys probes, and those probes aren't carrying sensors, they're carrying payloads. Bioweapons, nanotech, kinetic impactors, something designed to end the threat efficiently. And we find out in December when the probes arrive, and it's not first contact, it's last contact. The dark forest strikes and another clearing opens where a noisy civilization used to be. I don't think that's what's happening. I want to be clear about that. The evidence doesn't support imminent attack. 3I-ATLAS's trajectory, its behavior, the lack of obvious weaponization, none of it screams hostile intent. But the point of considering dark forest scenarios isn't to predict what will happen, it's to understand the worst case so we're not blindsided if it occurs. And the worst case is that Loeb is right about artificial origin and wrong about everything else. That this isn't exploration, isn't science, isn't even assessment for potential cooperation. It's the hunter in the dark forest lining up a shot, and we're the target that made too much noise. If that's real, if that's what's coming, we should at least see it clearly before it arrives. Because the alternative, being eliminated while still believing we're about to make peaceful first contact, is somehow worse than going down knowing what hit us. At least then we'd understand why the galaxy was so quiet. Not because no one's there, but because everyone who announced themselves got silenced. And we're about to learn that lesson the same way every other loud civilization did. By becoming another cautionary tale whispered in the dark forest, another reason for the next species to stay hidden and stay quiet and stay alive by never ever revealing themselves to the universe beyond. The gift, what benevolent contact could bring. Let's talk about the opposite scenario. Not the dark forest, not preemptive strikes and cosmic paranoia, but genuine benevolence. What if 3I-ATLAS represents a civilization that sees emerging species as opportunities rather than threats? That remembers what it was like to be young and alone and confused, that's decided helping others is worth the investment? It sounds naive after spending time in the dark forest, but it's not actually implausible. Evolution on Earth produced both cooperation and competition. We have predators and parasites, but we also have symbiosis, mutualism, species that benefit from helping each other. There's no reason alien evolution couldn't produce the same range of strategies, including ones that favour cooperation at cosmic scales. The biological argument for benevolence is actually pretty strong. If intelligence is rare, if the transition from single cells to technological civilization is so statistically unlikely that only a handful of species achieve it per galaxy, then each one that succeeds is valuable. Not economically valuable necessarily, though there might be trade opportunities, but valuable as fellow travellers, as other minds, as potential contributors to understanding and knowledge. When you're alone in the universe, or nearly alone, finding another intelligence is like finding another human in a vast empty desert. You don't immediately kill them out of paranoia. You treasure them because they're rare and precious and might be the only companion you ever meet. There's also the temporal argument. If a civilization survives long enough to become truly advanced, millions of years stable and expanding, they've probably figured out whatever was likely to kill them. Resource scarcity gets solved by accessing more resources. Internal conflict gets solved by whatever social structures prevent self-destruction. Existential threats from physics or astronomy get solved by technology or migration. At that point, what motivates you? Not survival. You've secured that. Maybe curiosity, maybe the drive to understand more of the universe. Maybe companionship, the desire for other minds to interact with. Maybe legacy, the satisfaction of helping younger species avoid the mistakes you made. These are human motivations, but they're not crazy to extrapolate. If anything, the longer you exist, the more existential and philosophical your motivations probably become. So let's imagine 3I-ATLAS is sent by that kind of civilization. They detected our signals, our radio bubble, or our nuclear testing, or our atmospheric changes, and they thought, here's another one, another species that made it to technology. Let's see if we can help them survive what comes next. They launch a probe, it travels for decades or centuries, it arrives now when we're in the critical window between capability and wisdom. And its mission isn't assessment for threat, it's assessment for contact. Are these beings ready to be told they're not alone? Will knowledge of aliens help them or destabilize them? What kind of contact would be most beneficial at their current development level? The direct contact scenario is the one that shows up in optimistic science fiction. A ship lands, beings emerge, they announce themselves, they offer technology and knowledge and partnership. But that's probably not how it would actually work, even with benevolent intentions. Anthropologists studying uncontacted tribes don't just walk into the village and start handing out smartphones. They observe first, sometimes for years, learning language and culture and context. Then maybe they make carefully staged contact, limited interaction that allows the tribe to adjust at their own pace. The goal isn't to transform the tribe overnight, it's to offer connection without destroying what makes them unique. Apply that methodology to interstellar contact and you get something more subtle than Hollywood depictions. Maybe the probes arrive but don't announce themselves immediately. They observe, they gather data about our languages and cultures and conflicts and capabilities. They assess our readiness not in abstract terms but specifically. Which nations or groups would respond well to contact? Which would respond poorly? How do we handle uncertainty and change? What are our existing frameworks for dealing with the unknown? All of that information helps calibrate how contact should proceed to minimize disruption and maximize benefit. Then maybe they start with indirect contact. Not landing on the White House lawn, but sending signals we can decode, mathematical sequences or images that prove intelligence without demanding immediate response. Let us process the reality of alien existence at our own pace. Let our scientists analyze the signals, let our governments deliberate. Let our populations adjust to the idea before pushing for face-to-face interaction. It's the slow approach, the one that respects our agency and our need to integrate paradigm shifts gradually, rather than all at once. Or maybe they decide direct technology transfer is the most helpful intervention. We're facing climate change, we need energy solutions. They could transmit blueprints for fusion reactors, for solar collection systems that are orders of magnitude more efficient than ours, for carbon sequestration technologies that actually work at scale, not built for us, not handed over ready-made, but given us knowledge that we implement ourselves. That preserves our autonomy, we're still solving our own problems, but we're doing it with better tools. It's like giving a struggling student access to better textbooks. They still have to do the work, but the resources make success more achievable. Medical technology would be transformative. If they understand biology at levels we don't, if they've solved aging or disease or genetic disorders, sharing that knowledge would save billions of lives. Not just human lives now, but all future humans who would otherwise die from conditions that become preventable. The ethical case for sharing medical technology is almost overwhelming. What kind of civilization has cures for cancer or Alzheimer's or genetic diseases and doesn't share them with species that are suffering? Even if there are risks, even if rapid life extension causes social disruption, the alternative is letting beings die when you could prevent it. The physics knowledge would reshape everything we think we know about the universe. If they have faster than light travel, or technology that looks like faster than light travel even if it technically isn't, the implications for physics are enormous. Either our understanding of relativity is wrong in ways we haven't discovered, or there are loopholes we haven't found, or the technology exploits phenomena we don't know exist. Any of those possibilities would revolutionize science, not just applied technology, but fundamental theory. We'd be rebuilding physics from principles they reveal, learning what the universe is actually like, rather than what we've been able to figure out from our limited perspective. The computational technology would be equally revolutionary. If they have artificial intelligence that's truly general, that's safe and aligned and beneficial, studying how they achieved that would help us navigate our own AI development. We're rushing toward artificial general intelligence without clear understanding of how to make it stable or beneficial. We're worried about alignment problems, about AI that optimizes for goals in ways that destroy what we value. If someone's already solved those problems, if they can show us architectures or training methods or governance structures that work, that's arguably the most valuable knowledge we could receive. It might prevent us from building AI that kills us, which would be a substantial gift. But let's talk about the less tangible benefits, the philosophical and psychological impact of confirmed benevolent contact. Knowing we're not alone changes human civilization fundamentally. It ends debates about whether intelligence is unique to Earth. It proves that life can develop elsewhere, that the universe is inhabited, that we're part of a broader community of minds. That's cosmically significant. It affects how we see ourselves, our place in the universe, our potential futures. It's the difference between being an isolated species on one planet and being part of something larger. Religions would adapt, some faster than others. The Catholic Church is already on record saying alien life doesn't contradict theology. Other denominations would probably follow, reinterpreting scripture to accommodate the new reality. You'd see new religious movements form around alien contact, maybe cargo cults, maybe entirely novel frameworks that incorporate both human spirituality and alien existence. But you'd also see religion decline in some populations. If aliens have been around for millions of years and don't seem to worship anything, that's data about whether religion serves eternal truth or cultural function. People would draw different conclusions, but the discourse would be informed by an existence proof that intelligence doesn't require religion. The political impact could be unifying. Faced with the reality of alien civilizations, human differences might seem less important. National borders, ethnic conflicts, ideological disputes, all of it takes place against a backdrop where we're one species among many. That perspective shift has potential to reduce internal conflicts, to push cooperation over competition, to make us realize we're all in this together in ways that matter more than what divides us. It's the overview effect astronauts describe, seeing Earth from space and recognizing how fragile and unified it looks. Contact would be the overview effect for the entire species, seeing ourselves from an outside perspective that makes the big picture unavoidable. Economic impacts are harder to predict but potentially massive. If technology transfer happens, entire industries become obsolete overnight. Fossil fuels would crash if we get better energy systems. Automotive manufacturers collapse if transport technology leapfrogs. But new industries emerge around implementing and adapting alien technology. It's creative destruction at civilizational scale. There would be winners and losers, upheaval and displacement, but the net effect long-term would probably be enormous wealth generation. Better technology means better resource extraction, better manufacturing, better distribution. The economy would grow, potentially dramatically, assuming we manage the transition without collapse. The social impact might be the hardest part. Not everyone would welcome contact. You'd have populations that see it as threat, invasion, corruption of human purity. You'd have groups demanding isolation, demanding we refuse alien technology and knowledge, insisting we develop on our own, or not at all. Those divisions could be violent. History suggests that when some groups embrace rapid change and others resist, you get conflict. Civil wars, terrorism, attempts to sabotage contact or punish those who engage with aliens. Managing that social fragmentation would require skill and patience that current governments mostly don't have. But if we navigate it, if we manage the transition from isolated species to contacted species without destroying ourselves in the process, the long-term future opens up in ways that were closed before. We'd know interstellar travel is possible because they did it. We'd have models for how stable spacefaring civilizations function. We'd potentially have allies, trading partners, sources of knowledge and assistance as we expand beyond Earth. We wouldn't be fumbling alone through cosmic dangers. We'd have guidance, or at least examples of what worked and what didn't. That's the gift scenario. Not technology alone, though that matters. Not knowledge alone, though that's valuable. The real gift would be context, perspective, knowing we're not unique or alone, being given a place in the larger story of intelligence in the universe. And here's the thing about benevolent contact that makes it plausible. Despite dark forest fears, it's self-reinforcing. If even one civilization in the galaxy decides to help younger species, if they're successful at it, then some of those younger species survive who would have died otherwise. And those species, having been helped, might adopt the same benevolent strategy when they encounter younger species themselves. You get a cascade, a culture of assistance that spreads not genetically but mimetically. The civilizations that survive are disproportionately the ones that were helped, and they pay it forward, and the galaxy gradually fills with cooperators rather than defectors. It's optimistic game theory, not because cooperation is guaranteed, but because it's stable once established, and it selects for its own continuation. Maybe that's what 3I-ATLAS represents. Not the first contact, but the next contact in a chain that stretches back millions of years, civilizations helping each other climb the ladder, making sure the young ones survive the Great Filter because they remember being helped through it themselves. It's a gift economy at cosmic scale. You can't repay the ones who helped you. They're too far ahead, too different. But you can help the ones behind you, the ones who need what you needed. And maybe that's enough. Maybe that's how intelligence survives in a universe that's mostly empty and cold and lethal. Not by hiding in the dark forest, but by lighting fires for each other, making sure nobody has to face the darkness alone. If that's what's coming, if that's what those probes carry, then December isn't a deadline for extinction. It's the beginning of everything we've been hoping for since we first looked at the stars and wondered if anyone was looking back. The Watcher, living under permanent observation. There's a scenario between extermination and embrace that might actually be more likely than either. 3I-ATLAS isn't here to destroy us or help us. It's here to watch. Permanent observation, establishing a presence in the solar system, not for immediate interaction but for long-term monitoring. It's the scientific station approach. When you discover an interesting phenomenon, you don't interact with it, you don't interfere, you just observe. You set up instruments, you record data, you watch what happens naturally. And humanity in 2025, teetering on technological emergence, facing climate change and AI development, and potential self-destruction, would be very interesting to watch. We're at a critical juncture, and someone might want a front-row seat for what happens next. The paper by Loeb, Hibbard and Crowell calculates that if 3I-ATLAS wanted to park in a stable orbit, Jupiter is the ideal location. The gravitational dynamics work well. You can maintain a position with minimal fuel expenditure, and you're far enough from the inner system to avoid detection while close enough to send probes for detailed observation. A Jupiter orbit also gives you time. You're not passing through on a hyperbolic trajectory, gone in months or years. You're staying indefinitely, able to watch developments over decades or centuries. If the mission is long-term monitoring rather than immediate assessment, that's what you choose. And the trajectory of 3I-ATLAS, with its close approach to Jupiter in March 2026, is consistent with that scenario. Think about what long-term observation would look like. Not a single probe that arrives and reports back, but a network. Multiple small satellites distributed through the solar system, maybe in stable orbits around various bodies, maybe in solar orbit at key locations, each one equipped with sensors, communication systems, enough intelligence to operate autonomously, or respond to instructions sent from the mothership. They wouldn't need to be large. A satellite the size of a washing machine could carry sophisticated instruments if you're working with advanced technology, and hundreds or thousands of them could monitor different aspects of human activity continuously. What would they watch? Electromagnetic emissions, definitely, all our radio and television and internet and radar, everything we broadcast. That tells them about our technology level, our communication patterns, what we talk about, what we value, how we organize information. They'd monitor atmospheric composition, tracking our industrial output, our carbon emissions, our pollution signatures. That tells them how we're affecting our environment, whether we're managing planetary systems sustainably or destroying them. They'd watch light signatures at night, seeing how cities grow, how populations shift, where energy use concentrates. That tells them about urbanization, development patterns, resource consumption. They'd probably watch military activity closely. Weapons testing, troop movements, naval deployments, all the indicators that nations use to track each other's capabilities and intentions. If you're assessing threat level, military capacity is key data. Are humans developing increasingly powerful weapons? Are they expanding into space with military assets? Are they showing signs of turning orbital infrastructure into weapons platforms? All of that would be logged, analysed, fed into models predicting our trajectory. They'd watch space activity with particular interest. Every launch, every satellite deployment, every probe sent to other planets. That tells them about our space program, our ambitions beyond Earth, how quickly we're developing the capability to become interplanetary. There's probably a threshold they care about, a point where we transition from Earth-bound civilization to solar system civilization. When we establish permanent bases on the Moon or Mars, when we start mining asteroids at scale, when our industrial capacity extends beyond one planet, we become a different kind of entity. More capable, more dangerous, potentially more interesting. Monitoring for that transition would be a priority, but they'd also watch social and cultural patterns. How do human civilizations rise and fall? What causes internal conflicts? How do we handle technological disruption? What happens when climate change stresses resources? Do we cooperate or fragment? Do we solve problems or collapse? These are questions you can't answer by studying one moment. You need longitudinal data. You need to watch across decades, seeing how the species responds to challenges over time. That's the kind of data that helps predict long-term trajectory, whether we're likely to survive and expand, or whether we'll destroy ourselves before reaching interstellar capability. The ethical questions around observation are complex. On one hand, we observe animals all the time. Wildlife cameras, tracking collars, ecological surveys. We study species without their consent or knowledge because we believe the knowledge gained justifies the intrusion. If aliens view us similarly as an interesting species worth studying but not equal partners in the decision of whether to be studied, then observation without consent might seem perfectly reasonable to them. We're the chimpanzees in the jungle, unaware that every behaviour is being logged by researchers with purposes we don't understand. On the other hand, we're not chimpanzees. We're self-aware, communicative, capable of understanding that we're being observed and having opinions about it. The ethical standard for studying intelligent beings is different than for studying animals. Human research ethics require informed consent, require that subjects understand what's being studied and agree to participate. If aliens subscribe to similar ethics, then observing us without announcement, without asking permission, would be a violation. Unless they conclude we're not sophisticated enough for those ethics to apply, that we're still in a developmental stage where observation for our own good justifies the lack of consent, that's paternalistic but may be defensible depending on their assessment of our maturity. The psychological impact of knowing we're being watched would be profound and varied. Some people would feel violated, surveilled without permission, studied like lab rats. The privacy concerns would be enormous. Everything humanity does, every communication, every decision, potentially recorded and analysed by alien intelligence. There's no privacy on a planetary scale if someone has satellites watching from orbit, with sensors we can't detect or interfere with. That breeds paranoia, distrust, the feeling that nothing is private anymore, that we're living in a cosmic panopticon. Others would feel reassured. If they're watching, maybe they're protective. Maybe their presence prevents other threats, other civilizations that might be hostile, because this system is already claimed or monitored. We're in a nature preserve, protected by the observers even if we don't know it. That's a comforting thought. It means we're not alone and vulnerable. We're alone and watched over. The universe isn't empty and indifferent. It's populated and someone's paying attention to us. That could be existentially soothing, even if it comes with surveillance. There would definitely be people who want to communicate with the watchers, who see observation as opportunity for contact. They'd try to signal, to send messages, to do things specifically designed to get reactions from whoever's watching. It would be like laboratory animals trying to communicate with researchers, performing behaviours that might elicit response. Some of that would be scientific, attempts to establish communication protocols. Some would be religious, seeing the watchers as gods or angels or cosmic parents. Some would be political, trying to leverage alien attention for factional advantage. The dynamics would be messy. Governments would face impossible dilemmas. Do you acknowledge the surveillance publicly? Do you tell populations that alien satellites are probably watching everything we do? That creates panic, social disruption, political instability. People don't like being watched, especially by entities they can't control or negotiate with. But keeping it secret, if the evidence becomes strong enough that secrecy isn't sustainable, breeds conspiracy theories and distrust. Either path has costs, and choosing between them requires predicting public response under unprecedented conditions. Most governments would probably default to secrecy as long as possible, then control disclosure when forced, but the transition would be chaotic. The strategic military question is whether you can or should try to interfere with surveillance. If you detect satellites watching you, do you attempt to disable them? There are arguments for yes. Surveillance gives the watcher enormous intelligence advantage. They know your capabilities, your defenses, your vulnerabilities. If conflict ever occurs, you're fighting from a position of complete information asymmetry. Denying them that advantage, even if you can't eliminate their technical superiority, might matter. And symbolically, destroying a surveillance satellite sends a message: we're not passive, we're not accepting this, we notice and will respond. That might deter further intrusion or establish that we demand respect even from more advanced civilizations. But the arguments against interference are stronger. If you destroy their satellites, you're escalating to conflict with a civilization vastly more capable than you. That's suicidal strategy. You might take out a few sensors, but you can't win the broader confrontation, and you've just announced hostility to someone who could crush you. Better to tolerate surveillance, gather what intelligence you can about their systems, prepare as best you can, but avoid provoking confrontation unless forced. It's the same logic smaller nations use when superpowers surveil them. You can't stop it, so you focus on what you can control, maintaining internal security and preparing for contingencies. There's also the possibility that this has been happening for a long time and we're just now noticing. The UFO phenomenon, the unexplained aerial sightings that military pilots and civilians report, maybe some fraction of those are surveillance drones from a long-term observation program. Not alien spacecraft in the sense of ships carrying beings, but automated probes, AI-controlled sensors, things that have been cycling through our atmosphere for decades or centuries, watching and recording. 3I-ATLAS wouldn't be establishing observation, it would be refreshing or upgrading an existing network. New mothership arrives, deploys newer technology, replaces old satellites with better ones, continues a program that predates human civilization. That reframes a lot of history. Were we watched during World War II? During the atomic bomb development? During the space race? If observation has been continuous, if there's a record of human civilization going back centuries, then they know us better than we know ourselves. They've seen patterns we're blind to, trends that only become visible across generations. They can predict our behavior with models trained on centuries of data. That makes us transparent to them in ways that are fundamentally asymmetric. We're guessing about their intentions with almost no information. They know our intentions, our capabilities, our trajectories with high confidence. That information imbalance is strategic nightmare, but it's also potential opportunity. If they've been watching long enough to understand us deeply, then they might also care about us in ways that come from familiarity. You don't watch something for centuries without developing some relationship to it, even if it's one-sided. Researchers who study animal populations for decades often become advocates for those animals, working to protect them, to preserve their habitats, to ensure their survival. Maybe long-term observation of humanity has produced similar dynamics. The watchers know us well enough to care what happens to us, to want us to survive, to intervene if we're about to destroy ourselves. Not because we've earned it, but because they've invested so much time observing us that our extinction would feel like personal loss. The observation scenario is frustrating because it's so uncertain. You know you're watched, but not why. You know there's presence, but not intentions. You can't force interaction, can't demand answers, can't even confirm the observation is happening unless they reveal themselves. And they might never reveal themselves. They might watch for centuries more, for millennia, recording human civilization from emergence to whatever comes next, extinction or transcendence or something between. We'd never know for sure if we're alone or observed. The uncertainty would become a permanent feature of human existence, something every generation grows up with but never resolves. Living under permanent observation would change how we think about privacy, about autonomy, about what it means to be human in a cosmos where we're subjects of study. Some people would adjust, accept it as new reality, incorporate it into their worldview. Others would resist, reject the premise, insist we're alone until proven otherwise. The division would persist across generations. And maybe that's the point. Maybe observation isn't just about gathering data on our technology or biology. Maybe it's about seeing how an intelligent species handles the knowledge that they're watched, how they adapt psychologically and socially to existence under surveillance. That's data you can't get any other way. You have to watch and see how they respond. If 3I-ATLAS parks at Jupiter, if it settles into stable orbit and stays, we'll face that question directly. Do we accept permanent watcher in our solar system? Do we try to communicate with it? Do we attempt to study it the way it studies us, turning observation into mutual exchange? Or do we pretend it's not there, live our lives as if we're still alone, let future generations deal with implications we're not ready to process? There's no right answer. There's only the choice each generation makes about how to live under eyes we can't see, being judged by standards we don't know, performing for an audience that never applauds or boos, just watches and takes notes and waits to see what we'll do next. The timeline. How we'll know what it really is. 4 days from now, on October 29, perihelion happens. 3I-ATLAS will be at its closest point to the Sun, 135 astronomical units out, moving at 68 kilometers per second, bathed in 33 gigawatts of solar radiation. And we won't see any of it. The object will be behind the Sun from Earth's perspective, hidden by the corona, invisible to every telescope in our network. The blackout continues through early November. Then the object emerges on the other side, and the real observation window opens. What happens in that window, what data we collect between November and March, will determine whether this story ends as interesting comet or as the most important event in human history. So let's map the timeline, mark the critical dates, understand what we're looking for, and when we'll know. November 4th, 2025 is the first major data point. The European Space Agency's JUICE spacecraft, the Jupiter Icy Moons Explorer, will pass within 64 million kilometers of 3I-ATLAS. That's close by space standards, close enough for detailed observations across multiple wavelengths. JUICE carries cameras, spectrometers, magnetometers, particle detectors, all designed for studying Jupiter and its moons, but perfectly capable of characterizing an interstellar visitor. The spacecraft will snap images, measure brightness variations, analyze light reflected from the surface or emitted from the coma if there is one. Spectroscopy will break down the chemical composition, looking for emissions from specific molecules, checking whether the abundances match cometary expectations, or whether we see more anomalies like the nickel without iron signature. What we're looking for on November 4th is change. If 3I-ATLAS went through perihelion and behaved like a comet should, we'll see evidence of intense outgassing. The heat from being that close to the Sun would vaporize massive amounts of ice, creating a bright coma, a prominent tail, a dramatic increase in activity. Comets that get that close typically become visible to naked eye from Earth. They're spectacular sky shows. If JUICE sees that, if the images show classic cometary features amplified by the perihelion passage, that's strong evidence for natural origin. The lobe scale rank would drop, maybe to 2, maybe lower. Still anomalies in size and trajectory, but behavior consistent with what comets do. If JUICE sees something else, if 3I-ATLAS looks the same as it did before perihelion, no increased activity, no obvious sublimation effects, no brightening despite absorbing gigawatts of solar energy, that's a problem for the comet hypothesis. Where did the energy go? If it's not heating ice and creating coma, what's it doing? That could indicate a rocky composition, more asteroid than comet, but then we're back to the size problem. Asteroids that large shouldn't be common as interstellar visitors, or it could indicate that the surface isn't reactive to solar heating in normal ways, that it's coated or shielded or composed of materials that don't sublimate easily. Any of those explanations raises more questions. The trajectory is what matters most. JUICE will measure 3I-ATLAS's position precisely, and ground-based observatories will be tracking it simultaneously. Those measurements get fed into orbital calculation software, predicting where the object should be based purely on gravitational forces. The Sun's gravity, the planet's gravity, relativistic effects, radiation pressure, all the factors that shape trajectories get modelled. Then you compare predictions to observations. If they match within error bars, the object is following natural physics. Gravity alone explains its motion. If they don't match, if there's deviation, you've detected non-gravitational acceleration. and that's the signature everyone's watching for. Non-gravitational acceleration can be natural. Comets experience it all the time from outgassing, the rocket effect of venting gas preferentially in one direction. But the magnitude and direction matter. If the acceleration is small and radial, pointing away from the sun, that's consistent with solar radiation pressure or outgassing. If it's large, or if it's not radial, if there's a component tangent to the orbit or perpendicular to the orbital plane, that requires different explanations. Outgassing doesn't produce strong tangential acceleration unless the comet is rotating in specific ways and venting asymmetrically. Radiation pressure only pushes away from the sun. If you see acceleration that doesn't fit those patterns, you need something else. And the something else that fits best is propulsion. Let's be specific about what propulsive non-gravitational acceleration would look like. If 3I-ATLAS executed a no-birth maneuver at perihelion, if it fired engines to slow down and stay bound to the solar system, we'd see the velocity after perihelion being lower than predicted. Not by a little, by a measurable amount, maybe a few kilometers per second difference. The orbital eccentricity would change. Instead of hyperbolic trajectory headed out to interstellar space, we'd see elliptical trajectory that stays bound to the sun. The period could be decades or centuries, but it would be finite, not infinite like an escape orbit. Alternatively, if 3I-ATLAS deployed probes, we might not see change to the mothership's trajectory, but we might detect the probes themselves. Small objects separating from the main body, each on slightly different trajectories. That's hard to spot because the probes would be tiny compared to the mothership, and they'd start far from Earth. But if they're approaching inner system targets, if they're headed toward Earth or Mars or Venus, they'll get brighter as they approach. We might spot them weeks before arrival, dim moving objects against the star field, trajectories that don't match any known asteroids or debris. The odds of detection are low, but they're not zero. Amateurs with backyard telescopes have found asteroids and comets. If probes are inbound, someone might notice. December 19th, 2025 is the next critical date. 3I-ATLAS reaches its closest approach to Earth, 1.8 astronomical units, about 270 million kilometers. That's roughly the distance between Earth and Mars at their closest. Far enough that it's not a threat, close enough that our best telescopes will get excellent views. Hubble, James Webb, Keck, Gemini, every major observatory will be pointing at it. We'll get the best images, the most detailed spectroscopy, the clearest characterization we've had. If there are features to see, surface structures, material properties, unusual emissions, December 19th is when we'll see them. This is also the window when probes, if they deployed, might arrive at Earth. Late November to early December, based on the trajectory calculations in the Loeb paper. If mini spacecraft separated from 3I-ATLAS at perihelion and burned toward Earth, they'd be arriving around this time. Detection would likely be accidental. Someone notices a moving object that doesn't correlate with known satellites or debris. Or maybe detection is intentional on their part. Maybe they reveal themselves, activate lights or transmitters, announce their presence instead of trying to stay hidden. Either way, if it happens, December will be when we know. What do we do if probes arrive? That's the question governments should be gaming out right now, but probably aren't. Do you attempt interception? Do you try to communicate? Do you track and observe without interfering? The decision tree is complicated and time-sensitive. If you see something approaching and you have hours or days to respond, you need pre-planned protocols. But we don't have those protocols because we've never needed them before. The decision would get made in real time by whoever happens to be an authority when it occurs, based on incomplete information and political pressures. It would be improvised, messy, probably suboptimal. That's terrifying given the stakes, but it's realistic given how human institutions function under unprecedented stress. March 16th, 2026 is the final major observation opportunity. 3I-ATLAS passes within 54 million kilometers of Jupiter, close enough that NASA's Juno spacecraft can observe it. Juno has instruments optimized for studying Jupiter's magnetic field and atmosphere, but it can point at other targets. We'll get radio observations, infrared data, particle measurements, different wavelengths than we've had before, and critically this is 5 months after perihelion, 5 months after any O-birth maneuver would have occurred. By March, if the trajectory changed, we'll know definitively. The orbital elements will be refined to high precision. If 3I-ATLAS is still on escape trajectory, still headed out to interstellar space, the technological hypothesis weakens. If it's in bound orbit, If it's captured by the Sun's gravity or Jupiter's gravity, the technological hypothesis strengthens dramatically. Jupiter capture is particularly interesting. Getting captured by Jupiter requires precise trajectory design. You have to approach at the right angle, at the right speed, thread through the resonances and perturbations without getting ejected. It's hard to do naturally. Most objects that approach Jupiter either fly past and continue or crash into it. Settling into stable Jupiter orbit is unlikely by chance. If 3I-ATLAS achieves that, if it parks itself around Jupiter after March, that's almost impossible to explain without invoking deliberate maneuvering. And Jupiter orbit makes strategic sense for long-term observation. You're in the outer system, safely away from inner planets, in position to deploy probes to anywhere in the solar system, with access to Jupiter's moons for resources if you need them. It's where you'd choose to establish a permanent base if you wanted to watch the solar system long-term. Between these three major observation points, November, December, March, ground-based telescopes will be tracking continuously. Every night it's above the horizon, someone will be imaging it, measuring brightness, checking position. The data accumulates, uncertainties shrink, models improve. By April 2026, we'll have trajectory solution accurate enough to predict its position decades into the future. We'll know if it's staying or leaving. We'll know if the anomalies persist or resolve. We'll have spectroscopic data across months, showing how composition and activity change with distance from the Sun. All of that together will paint a picture much clearer than what we have now. And here's the critical thing. Science works on this timeline whether or not Loeb is right about artificial origin. If 3I-ATLAS is natural, if all the anomalies have explanations we haven't figured out yet, the observations between November and March will help clarify those explanations. We'll learn about interstellar comet composition, about how objects form in other stellar systems, about dynamics of ejection and interstellar travel. It's good science regardless. But if Loeb is right, if there's any truth to the technological hypothesis, the same observations will reveal that. The data doesn't care about expectations. It just is what it is. We point instruments, collect photons, measure positions, and the universe tells us its truth whether we're ready to hear it or not. Loeb has said that if 3I-ATLAS shows normal cometary behavior, post-perihelion, he'll lower its ranking on his scale. He's not wedded to the alien hypothesis. He's responding to evidence. That's how science should work. You form hypotheses based on available data, you make predictions about what future data will show, and you adjust beliefs when new data comes in. The problem is that public discourse doesn't work that way. Once people latch onto narrative, contradicting evidence often strengthens belief rather than weakening it. If 3I-ATLAS turns out to be natural, there will still be communities convinced it was alien, that the evidence was suppressed or misinterpreted, or that scientists are lying. That's frustrating but inevitable. On the other hand, if evidence accumulates toward artificial origin, if trajectory changes appear, if probes are detected, if by April the preponderance of data suggests this isn't natural, then consensus will shift. Slowly, grudgingly, with holdouts and deniers, but it will shift. Because ultimately reality constrains belief. You can deny that Earth orbits the Sun, but the predictions based on heliocentric model work and geocentric predictions don't. You can deny that 3I-ATLAS is artificial, but if it's maneuvering and deploying probes and parking in Jupiter orbit, at some point denial becomes untenable. The evidence would become overwhelming. We're 4 days from the beginning of that evidence collection. 4 days until perihelion, the hidden moment when everything might change. Then weeks of waiting for JUICE data, for first observations post-blackout, for trajectory refinement. Then December's close approach, the window when probes might arrive or when we get definitive images showing natural features. Then March's Jupiter encounter, the final major data point before we're just watching it recede into distance. 6 months total from perihelion to Jupiter, from October 29th to March 16th. That's the timeline. That's the window when we'll know. And knowing will change things regardless of what we learn. If it's natural, we'll have studied an interstellar object in unprecedented detail, learned things about planetary formation in other systems, tested theories of cometary behavior under extreme conditions. If it's artificial, we'll have confirmed we're not alone, begun the process of understanding what that means, started adapting to a universe that's inhabited and watching. Either outcome reshapes our future. Either outcome makes these 6 months historically significant. We're living through the observation period that will be analysed for centuries. Future humans will look back at late 2025 and ask, what did they see? What did they miss? How did they respond? And the answers to those questions are being written now, in telescope images and trajectory calculations, and the decisions we make about how to interpret data that's just starting to come in. 4 days until perihelion, 3 weeks until JUICE, 7 weeks until Earth closest approach, 21 weeks until Jupiter encounter. The clock is running, the observation window is opening, and whatever 3I-ATLAS really is, whether comet or spacecraft or something we don't have words for yet, we're about to find out. Not through speculation or analysis of old data, but through fresh observations, real-time measurements, evidence collected while it's happening rather than reconstructed from traces. This is science in the moment, history being made while we watch. And all we have to do is wait and look and be ready for whatever the data reveals. Because ready or not, the answers are coming.